Good afternoon. My name is Vasic, and Professor Narayanan Rengaswamy and I will be giving this lecture on classical and quantum error correction. As you heard from previous lectures, our quantum bits are sensitive to errors and noise, and they have to be protected. So in this course, we will learn methods how to protect errors, how to protect qubits. And this lecture has two parts. In first part, we will address classical error correction. Quantum error correction is based on coding theory, classical coding theory. So in the first part, I'll cover basis of classical codes. And then in the second part, Professor Rengaswamy will cover quantum error correction and quantum codes. So we'll have also Nitin and Asit who can answer your questions in the poll. In the chat, I'm sorry, and then also there will be poll questions from here and there, and if you have questions about the poll questions or you are not sure, they can also answer these. So with this, let me share the screen. Hopefully you can see it, and then we can start. So let's start with let's start with classical error correction. So we consider digital communication system or storage system in which two users communicate. So the first user tries to send some message. Let's say it is a phone message. So to I don't know, his girlfriend. He's obviously in Arizona, and she is in New York because it is dark, as you can see. So the first step so it is done over a communication system, and the first part of this communication is that we convert the voice or analog signal to a binary format. So 2 bits, and then we count that there will be errors in the system, and then these bits we protected by error correction encoder, and then we first modulate the signal and then send it to a communication medium or a channel over which we really don't have a control, and it introduces noise, distortion, and interference, all kinds of disturbances to the signal. So our goal at the receiver, which is shown at the bottom, is to recover the signal. So we first go and demodulate and detect the signal, and then and convert it to binary string. And then do error correction decoding, and then convert these binary strings to analog signal. So the way that we do this practically is the modulator converts our sequence of binary zeros and ones into a waveform, analog waveform. And in this plot, I show that ones are represented by a cosine signal of a higher frequency, and zeros are represented as a, let's say, cosine signal of lower frequency. So this is a modulated signal that I show. It is a time and amplitude of this signal. Of course, there are many different types of modulation, and for our purposes, for error correction, it is sufficient to understand this. So our detected signal should be actually 0, 1, 0. But in the detector, we put maybe some filters, and we try to recover these rectangular pulses that are originally sent, but we don't get ideal pulses. We get something else, these distorted or noisy pulses. And what we can do is we can take a sample at the middle of each bit interval in time. And you see these green lines that I'm showing are these samples. So you see how sample for first one is large, a sample for the second is relatively small, and then for one we should have a larger sample, but we get a lower sample. So then we can put a threshold and compare whether these samples are large or small, and then you see that because of the fact that this sample at the last bit, third bit, is lower than the threshold, the detector produces as an output 0, which is of course an error. So therefore we transmitted 3 bits, and then the third bit is transmitted in error. So what we do is for the purpose of error correction, we make an abstraction, and then we don't consider in our course any modulation or reduction. So the model that we have is the following. So we have a sequence of bits that go into a communication channel, and then we have some output of the channel, and this channel output is not necessarily the same as input. Ideally, it is the same, but for example, here we show that there is one error. So what is the channel? We describe the channel by a statistical model. So let's suppose that x1, x2, x3, and x4, etc. are input bits. These are zeros and ones, and y1, y2, y3, y4, etc. are channel outputs. And for now, we can assume that these are also bits, or that they don't have to be bits. They can be some real numbers. So the channel is described by probability density function of output given input. And in our course, we will consider the simplest channel, which doesn't introduce any memory, where transmission of signal of a bit x1 and x2 is independent of each other. So we get y1 bit as a result of the bit x1, but it is not affected by other bits. So in other words, this conditional density function of, let's say, n output bits given n input bits can be written as a product of individual conditional densities of ith input and output and input. So what we have is we will consider several simple models. Of course, our channel is complicated in practice, but for us, for our purposes, we can consider different these channel models. So in the first model, we assume that input they're represented as these graphs, oriented graphs. So the vertices on the left denote input symbols, and vertices on the right denote output symbols. So for the first channel that we consider which is binary erasure channel, there are 2 inputs, binary inputs, 0 and 1, and but at the output we can have 3 symbols, 0 or 1. So this means and a special symbol that we call the erasure. So these numbers here on the edges denote probability. So this 1 minus epsilon, think of epsilon as some small number, and this 1 minus epsilon is a probability that when I transmit 0, I receive 0. So you see, when I transmit 0, there is a small probability that I get an erasure, this erase symbol. And it is important to notice that here we know that there was an error, that there was erasure. So when I receive some symbol E, I know that that it is either 0 or 1, but I don't know what it is. But I know that the channel didn't transmit correctly the symbol. So you see, there are no really errors, there are just erasures. When I transmit 0, I always receive either 0 or erasure. I never receive 1. This is different in this other model that we call binary symmetric channel model, where it is possible to make error. When I transmit 0, it is possible to receive either 0 or 1, and this happens with probability 1 minus alpha and alpha. So alpha is probability of error, and 1 minus alpha is probability of a correct transmission. So the channel is called symmetric because it is the same probability that that bit 0 is flipped to 1, or that bit 1 is flipped to 0. And it is a binary because the inputs are and outputs are binary. And so finally, we have this third channel model that is very often used, that we call the additive white Gaussian noise model. So again, inputs are binary. So this, I represented them as 0 and 1, but after these 0 and 1s are modulated, it can be represented by some other amplitudes. But the output is now continuous. Output symbol is some real number from minus infinity to plus infinity, and the channel is described by probability density function. The density function of an output y given input 0, and density of output y given input 1. And these densities are Gaussian with variance sigma square. So what is important that for each of these channel models, it is possible to define information throughput. So you see, if I transmit binary bits, if errors happen, obviously not all information that is on the input is transferred to the channel. And the laws of this is described by information theory. We are not going to discuss information theory in this course, but we know that there is some information loss in the channel under this uncertainty that we described. So the easiest thing to see is, it is easiest to see this on the example of binary erasure channel. So we know that epsilon fraction of bits are lost, and obviously the fraction of bits that is passed through the channel is 1 minus epsilon. So this is what we call the channel capacity. So this channel capacity is maximum information that can pass through the channel, and it has a very important meaning out for error correction. It will, for error correction codes, this value C will determine the highest rate of the code that we can design for this channel. So now this is the first question for you to see what we understood. Let's suppose that we have n symbols, and let's say these n symbols I organize and I call them a code word. And they're transmitted over a memoryless channel. And let's suppose that Y is the corresponding channel output. So, so this is a memoryless channel, and the question is, the conditional probability, the density of output given input can be written as one of these expressions. So maybe you can choose which one. Okay. So I'll skip to the next slide, and Narayanan or Asit and Nitin can answer the question. So of course the correct answer is B, as most of you guessed. As we said, that it can be written as a product of individual densities. So now, of course, now we have this channel. We are transmitting binary sequence and receiving some potentially incorrect sequence. And the question is, what do we do? How do we protect information? So clearly, if I transmit a binary sequence and I don't protect it by anything, there is no way for the detector, for the decoder at the output to say what is correct, what is incorrect. So if there is really error here on 0, and I don't know where it is, I don't know. There is nothing in the sequence that can tell me how to correct errors. So the basic idea of error correction is to add some redundancy. And here is the very simple and naive way to do it. So, and it is called the repetition code. So what we do is, the idea is instead of sending 1 or 0, we are sending 3 ones or 3 zeros. So every symbol 1 or 0 are repeated 3 times. So now it is transmitted over the channel, and you see that now if there is a single error in the in this triple, in 3 bits, that this error can be now corrected. The end correction can be done simply by majority rule. So if in the group of 3 bits I have more zeros than ones, I will decide that 0 was transmitted. So these zeros here are actually user bits, and these bits here, these triples, are channel bits. In quantum error correction, we will call these logical bits, and this will be physical bits. So you immediately see the problem of this transmission. So this scheme will be able to correct a single error in 3 bits. But what happens if I have more than a single bit in a group of 3 bits? Obviously, I won't be able to correct, but the solution can be that I repeat a bit more than 3 times. So in this repetition coding, I can repeat maybe bit 5 times or 7 times or 101 times. And you see that I will be able to correct more and more errors. But the problem is, of course, that I'm repeating a bit. So in these 101 bits, or channel bits, I'm actually transmitting just 1 logical bit or 1 user bit. So this is obviously not good and not scalable. And we would like to find some other method in which we will transmit more user bits per use of the channel. So here we use channel 3 times in our example, but transmitted only a single bit. So what we do fortunately, the theoretical, we know that there is a theory that tells us that this is possible, that we can transmit more, that we can make the error correction scheme more efficient. And the way that we do is the following. So we have k message bits, and then we add some redundant bits to create a code word that has n bits. So k is smaller than n. So we added some redundancy. And we describe the efficiency of our scheme as by a code rate. And this rate is defined as a ratio of logical or information bits through number of physical bits. And from information theory, we know that this rate must be smaller than capacity of the channel. So coding theory actually tells us that how to construct these mappings between message and code words, and how to design decoders that will map receive words to code word estimates X or message estimates M. The role of our decoder is to it tries to estimate transmitted code word or transmitted message from received vector Y, so that the probability of bit or code word error is minimal. So this is the goal of our error correction scheme. So in order to do this, the decoder has to find the code word that is in some sense closest to received vector Y. So again, I want to remind you, this vector Y can be a binary vector of length n, or it can be real vector, or even a complex vector of length n. So now in the next couple of slides, we will give some ideas of how we do this. So remember, encoder maps k bits into n bits, and obviously one way to realize encoder is to write a lookup table. So this lookup table can have as input all possible combinations of these k bits and corresponding code words. But you see that it would be inefficient because the lookup table should be very large. So if I have k to be, I don't know, 100 or 1,000, which is typically practice in the case in practice, you'll see that the size of this lookup table will be 2 to the 100 or 2 to the 1,000, depending on k, which is impractical. So because of this, we use another idea, and we choose a mapping between message bits and code words to be a linear. So this is what we do. We take message M and multiply it by some matrix G, and to create a code word X. So information theory and coding theory tell us that the fact that we are doing this linear mapping still allow us to design good codes and, as you will see later, good decoders. So what is a generator matrix? Think of a generator matrix as this rows, arrangement of rows G1, G2 to Gk, where each row is a vector of length n. So what we do is we create code word X by a linear combination of rows of G. So M1 multiplies first row, M2 multiplies the second row, etc. So you see, since M1, M2, and Mk are really 0 or 1, the presence of 1 in the message means that I should take this row and put it in this linear combination, and absence of Mi0 means that I don't take corresponding row. So, by the way, these all operations, these plus operations are actually XOR operations, and these multiplications are multiplications on binary domain. So here is the first example, our repetition code. So I want to repeat bit n times. So what do? Is I have a generator matrix that contains just a single row, all ones, and message contains just one bit. So what I do is I just multiply m and g, and I create all code bits are actually equal to m. So here is another example of code that has 5 bits and has 2 information bits. So the code contains all possible, contains 4 code words. How do I create code words from rows of G? So I do what I just said. When M0 and M0 and M1 and M0 are 0, I don't select any of these rows, and I just actually select zeros, and so code word is 0. When the second bit is 1, I select the second row and I create a code word. When the first bit is 1, I select the first row, and when both are 1, I add these 2 rows and create a code word. So this is, you see, it is a very simple way of encoding data. So what do I do now? So you see what I actually did here. You see that in this generator matrix, I have identity matrix here, and I have some other things here. So you see that the first two bits in the code words are equal to the message bits, and the rest of bits are obtained as some functions, some linear functions of these message bits. For this way of writing generator matrix, we say that it is a systematic. So the code generator matrix is given in a systematic form because this identity matrix is isolated here on the left. So as I said, first and second bit are message bits, and the other 3 bits are dependent on these message bits and can be written as some linear combinations of these. So we can write expressions for these bits, and as you can see, I can create 3. Each of these bits, when I add it to itself, because it is XOR, it must sum to 0. So M1 plus M2 sum twice, XOR twice must be 0, and 2 XOR twice must be 0, and 1 XOR twice must be 0. So this is how we create these syndromes, values S1 and S2 and S3, and then of course there must be 0. So based on this,
Bane, quick comment. Are you using your mouse pointer? Because if you're using it, yeah, we are seeing it now.
Can you see it now?
Yeah.
Okay. Because I look at my other screen.
Yeah.
Okay. All right. So you see, I can create these values S1 and S2 and S3. So you see, M1 plus M2 plus M1 plus M2 must be 0 because this is all XOR, and the same thing for this value. So you see that S1 and S2 and S3 are actually equal to 0. So this gives rise to what we call the syndrome. So what we create is create a new matrix based on generator matrix. We create a so-called parity-check matrix. And when I multiply parity-check matrix to a code word, you see that here S1 and S2 and S3 can be expressed through message bits, but they can be also expressed through coded bits. So if I express it through coded bits, you see that I create a syndrome and this vector S, and if this is a code word, then all the values must be, all the values of S must be zeros. So the way that I created parity-check matrix here is, you see that I took this orange matrix here, and then I transport it, and I put identity matrix here. So this is also parity-check matrix that is written in a systematic form. So what we can see that since code word is obtained as multiplying M and G, then and I know that parity-check matrix times X transpose must be 0 for any message vector N, then we have a condition that H and G transpose is 0. So this is a condition that tells me how to create parity-check matrix from a generator matrix and how to create generator matrix if a parity-check matrix is given. So basically, I can do this by Gaussian elimination. So, so here is another question. So remember, we have k information bits, and we added some extra parity bits to create a code word of length n. And then we have a parity check matrix that checks whether whether linear combinations of bits are computed correctly. And this parity check matrix is a system of linear equations, and we the question is, what is the number of equations and what is the in this system. Okay, so maybe you answer. So maybe I move to the next slide. Now this syndrome will be used to correct errors. And the first illustration that I have here is correcting an erasure. So so you remember that I have a system of linear equations, and that so what I did is now some of this code word is transmitted. I have a parity check matrix here, and I can compute a syndrome that is 0. But now let's suppose that I transmit a code word X through a channel, and let's say it is a binary erasure channel. So some of the bits in Y are erased. So let's suppose that E is that the second bit is erased. So obviously, if I look at the code book, and I can see that if I have these 3 bits, these other bits to be 1, 0, 0, 1, that it is most likely that it is this erasure, that this bit is in erasure. But the question is, how do I do this using a parity check matrix? So you see that in parity check matrix, I need to find a linear equation that will have 1, that it will involve the second bit. And since all other bits are known, this parity check equation can be used to recover this this bit. So in other words, if in our example, since this first equation contains 1, this first equation can be used to recover this first bit. Now, what happens if I have 2 erasures? Then obviously I have to do something better. So I can maybe use the first linear equation to recover the first bit. And then after I recover the first bit, I can then recover the second bit by using some other linear equations or combination of linear equations. So however, in the case of binary symmetric channel, we cannot do this in this recursive way, just recovering one erasure by another. What we have to do is find error vector, and this error vector I can find from the syndrome. So imagine that received vector is incorrect, so that code word plus E is what I received. So by multiplying this output vector with the parity check matrix, now I'm not going to get a 0 syndrome. I'm going to get some other value, some other vector S. And in this case, this syndrome will be non-zero, and this non-zero syndrome is an indication that there is some error, and this error, I need to design some decoding rule to recover this error from the syndrome. How we do this, we will explain later. But what is important now is this abstraction. I like to think of my code words as subspace in some vector space of dimension n. So these points that I'm showing here are all possible words of length n. There will be 2 to the n of them. And some of these points are actually code words, and some of them are not code words. So I'm talking about, let's say, binary symmetric channel. So what I need to do is to somehow make decision region around each code word, so that when I receive any word, that I know which code word is transmitted. So obviously, these if these vectors corresponds to words that are close in some sense to these transmitted code words. In other words, they correspond to words that have a small number of bit flips compared to what was transmitted. So here is another poll question. So let's suppose that this is a parity check matrix, and this is the channel output. What is the syndrome?
Bane, just wanted to mention, so I mean, after each question, maybe we give a few minutes depending on the question, and then I think it's good to display the poll results. So maybe you can tell Brianna when to close the poll, and then she will show the results.
Yes, I don't know how to display. So Brianna, I guess Brianna can display it.
Yes, yes.
Okay.
Yeah, she said there is some problem, I guess. They're trying to fix it in showing the poll result.
Mm-hmm. Okay, so Brianna, maybe I can close poll, and I still don't see the. I cannot see the. Now I can see. So maybe I say what how we compute the syndrome. So remember, we multiply H with Y transpose, but what it we multiply H with Y transpose. But what does this practically mean? This means that for every one that is in receive vector, this one selects a column of H, and this multiplication is really adding columns of a parity check matrix, depending on whether I have one in a vector or not. So if I have, let's say, this vector y, this means that I will be adding first and two last columns of H, and this is how I would create a syndrome. Okay, so let's continue. So now, with this geometric interpretation of code, we know that. So let's imagine that these are code words, and in this space, vector space, and let's say that these white circles are some other vectors. So obviously, I would like these code words to be not very similar. So this distance that I described, that I show here, is actually number of bits in which they differ. So this is called Hamming distance, the number of positions in which two binary vectors differ. So you see that performance of the code, as you will see later, will be determined by the closest code words, or the distance between closest code words. So minimum distance we described as the Hamming distance between the two closest code words. So here is an illustration of our code. Remember, these are different code words. This is a parity check matrix. So now what I can do is I can create a table. I can find the minimum distance between each of these code words. So code word x1 and x2 differ in 3 bits, these 3 bits. x1 and x3 again differ in 3 bits. x1 and x4 differ in 4 bits. So these corresponding distances are 3, 3, and 4. And obviously the minimum distance is 3. So you can verify for this code that there are some code words that are at minimum distance and some code words that are on larger distance. So this code is a code that encodes 2 message bits into 5 coded bits and has minimum distance d equals to 3. So geometrically speaking, now again, if this geometrical representation actually can give me intuition how many errors I can correct. So for example, if I have a code word here and I put a sphere around this code word, so this sphere is a set of all points that are at Hamming distance at most 1. So if I put another sphere here around this code word of distance 1, so you see if I transmit this code word and receive any of these words will be closer to this code word than to this one, and they can be corrected. They can be correctly decoded. If I transmit, let's say, this code word, but there are 2 errors, I receive this word, then obviously this word is closer to this code word than to this one, and obviously it will be decoded incorrectly. So it is then we have this rule for codes that will have a radius t around the code word. So we can obviously correct any single error. We can correct 2 erasures because these 2 erasures can be recovered from these parity check equations, and we know that they are not errors. And because then we can detect 2 errors in this case, because the syndrome are not going to be 0 for these 2 errors. If I have more than 3 errors, if I have 4 errors, 3 errors, then one code word will be mapped, it will be incorrectly transmitted as another code word. And for this other code word, for the decoder, there is no way, the syndrome will be 0, and the decoder doesn't have a way to detect that there is an error. So this is important to remember, this error correction capability of a code based on minimum distance, that we can correct approximately half of the minimum distance of errors and d-1 erasures and detect d-1 errors. So here is now we come to the concept of a dual code that Narayanan will be using in quantum error correction. So dual code is described. So if G is a generator matrix of a code, we'll say that H is a generator matrix of a dual code. So remember this formula of orthogonality. So if I have a code C that are code words X to 4, I will have a dual code as a set of code words that will satisfy this equation, that will be orthogonal to, so each of these code words will be orthogonal to each of these codes in our code. So this set of code words forms a dual code. So for our code 5,2,3 code, we have code that has, again, 5 bits, that has 3 n-k 3 message bits for a dual code, and the distance by checking here the distance between code word, that is 2. So now, what is the connection between so far we understand how to protect information. We have also a description of how to simply correct errors. And again, we can have this geometric representation of code. So imagine that these are code words in my subspace of a vector space of dimension n. So I can represent this as this subspace. So this plane correspond to this subspace, and all code words are designed. The code is designed that all code words must belong to this subspace. So, and then the dual code. So the basis vectors of a code C are generator, are rows of generator matrix, and basis of a dual codes are vectors H1 to are vectors H of a dual code. So in our case, in our illustration, there is just one dimension for this dual space for H. So you see now, any point in the subspace can be obtained as a linear combination of basis vectors, rows of G, and these vectors in a dual space will be orthogonal to each of these vectors G, and therefore to any linear combinations of vectors G. So now you see that this would be now a good way to verify whether there is an error. So if I received a code word, the code word, when I project it to vector H to any of the orthogonal vector, result will be 0, and this indicates correct transmission. So this is so any code word here will result to 0. So this corresponds to 0 syndrome. However, if I have an error and I transmit a code word in this subspace, but I received a code word that is not in this subspace, then projection to H1 will result to a code word that will result to a syndrome that is non-zero. So this non-zero syndrome is indication that there is an error, and that this error now needs to be corrected. So here is another poll question for to determine what number of errors we can correct. So a linear block code with minimum distance d can correct how many
So when you ask Brianna to close the poll, so the poll results don't show the right answer. So maybe just quickly specify what the correct answer is. And then if there are more questions, we will handle it in the chat.
Mm-hmm.
So there's a question in the chat. So somebody is asking, what is weight in this case?
So weight is the number of errors, number of ones, binary ones in an error. So remember, Hamming weight of a code word we defined as a number of ones. Hamming distance between code words we defined and the number of flips. So the answer to this question is that we can correct the -1/2 errors. Sorry, so I did something. Sorry, I pressed something incorrectly. Okay, so what I can do is I have a couple of slides illustrating some codes with and illustrating how many errors we can correct. But in the interest of time, I will skip some of these slides, and I think the problem of how to correct errors is clear. So what I can do is so let's say that so I think it is clear that if the minimum distance of the code is 3, that they can correct a single error. This is what we established. One thing that we didn't say is how to do it. So what what we need to describe is actually what is our goal. So remember that earlier we said that the goal of error correction is to find estimate of a code word that is somehow closest to received vector. So what does it mean, closest? So we remember, one thing that we have is, let's say this is a binary symmetric channel, and then we have X and Y, X that is transmitted and Y that was received. So obviously, error correction capability of whether we can correct errors or not depends on in how many bits X and Y differ. So this is what we describe as a Hamming distance between X and Y. Remember, in the repetition code, we say that we can correct many errors. And in this example previously, we showed that we can correct a single error. And we really didn't describe how to correct more errors and what conditions and how we practically describe how we practically do this. But before we do this, we let's clarify the statement about the closeness. So remember, we said that the decoder needs to find an estimate of a code word that is closest somehow to Y, to receive vector Y. So in order to describe this, write a conditional probability of receive vector Y given transmitted vector X. Remember, in binary symmetric channel, flips happens independently with probability alpha. And let's suppose that the distance between X and Y is D. So this means that there are D flips that happen during transmission. So with probability alpha to the D, we have these flips, and the rest of the bits are not flips. So, and since they're independent, I can multiply this probability. So now, what is the best that the decoder can do? Our decoder needs to find, go over all possible input vectors X, all code words, and find the vector X that maximizes probability P of transmitting X given Y. So see, this is something that is given by the channel, and this is a probability that I need to compute. So the argument of X that the argument of this P that maximizes this P is estimate of the vector, and this is what is called maximum likelihood decoding rule, because it finds it maximizes likelihood of this code word. So I hope you remember Bayes' formula, and that this conditional probability can be written by in this way, where P of X is probability of input code word, P of Y is probability of output code word, and this P is probability that is given by this formula. So you see now, in order to find X, we have to maximize this, but you see that this P of Y doesn't depend on X. And if P of X is, if code word X are all equally likely, then maximization needs to be performed only on this conditional probability. So therefore, instead of maximizing P of X, I can use some convex function, and I can try to maximize log 2 of P of X, of this conditional probability. So remember what is conditional probability. So again, I'm rewriting what I'm trying to find. I take logarithm of this conditional probability. I need to find X that maximizes. So since P of X is this, when I take logarithm, you see that we have two terms. So D log 2 of D. Alpha is, remember, is some probability. Think of this as a small number. And I have n minus D log 2 of 1 minus alpha. So I can group the terms next to D and terms next to n. And you see that this part here doesn't depend on D, doesn't depend on the code word, and this part depends on D, depends on the code word. This alpha is a small number, so alpha minus alpha, 1 minus alpha is smaller than 1/2, so therefore this is a negative value. So maximizing this log actually corresponds to find a code word that maximizes, maximizing this means finding a code word that has minimal D. So this minimal D means that I need to find a code word that is closest to code word that is closest to received word in Hamming sense. So this is the D that describes the Hamming distance between the code words. So I'm going to skip these slides, but how do I do this? How do I do this practically? How do I can do in principle? So let's consider this code, and with this parity check matrix. So what I can do is to write this what is called standard array. So I can create a table that has 2 to the k columns, and in each column, in the first row, these are all code words, and in each column, in the first column, I will write low weight error patterns. So there will be, and in each other column, I will add this error pattern to a corresponding code words. So you see that in overall, there is 2 to the n possible code words. And you see that in this way, I divided all this space, all these vectors, 2 to the n vectors, into groups of 2 to the k vectors, and I can perform the decoding. On this right-hand side, I wrote a corresponding syndrome. So for a code word, of course, syndrome is 0, and when I have errors, the syndromes are non-zero. So now, what happens if I received a vector 1, 1, 0, 1, 0, this vector. Obviously, this is not a code word, but I can look into a standard array and find the code word that is the corresponding code word, the code word that is closest to this received vector. So you can see that in the standard array, this all these vectors are closer to this code word than to any other code word, and all these vectors are closer to this other to this code word than to any other code word. So vectors in the columns are closest. So of course the problem with this is that this is not practical, and the complexity of such decoder, of this standard array decoder, scales exponentially, because it will have 2 to the k rows and 2 to the n minus k columns. So we have to find something simpler. So here is the poll question, and I understand that I went over this slide quickly, but here is the standard array of a linear block code, and it has these code words, and these are error vectors. And the word that is transmitted is this, and the standard array decoders is used to estimate the transmitted code word. So what is the transmitted code word? That is the question. So if you look, the transmitted code word is this one. As most of you guessed correctly. Okay. So now we actually show a simple way to decode, and we say, and we explain how this is not scalable because of complexity of this lookup table. So in past decade or so, or 2 decades, there is a group of codes that was developed, and these codes are now widely used in many applications, and these are all described by graphs, and decoder algorithms are also described on as message passing algorithms on the graph. So in the next couple of slides, I'll try to explain how we decode these codes on graphs. And the most important class of these codes are so-called low-density parity-check codes. Later on, Narayanan will talk also about surface codes, and these codes can be also represented as codes on graphs. So now, remember that earlier we wrote that we introduced parity-check matrix, and this parity-check matrix introduces a system of linear equations between coded bits. And we know that if these V's are, so in this case, there are 7 bits, and let's say these 7 bits are correctly transmitted, so these are code words. So we know that there will be some linear combinations, and these linear combinations are given by a parity-check matrix that will result in zeros. So this linear combination, these linear equations, we will call them checks. So there are 3 checks here corresponding to 3 linear equations, and there are 7 bits. So for every parity-check matrix, for every system of linear equations, I can construct a graph that will contain 2 groups of nodes. So these circles correspond to variables or to bits, and checks or these squares correspond to parity checks or to check equations. So there are 3 of them. And so this graph is bipartite, and there are connections only between circles and squares. And we draw a connection if variables involved in a check. So, for example, if I look at variable v1, let's say check c1, it involves variables v1, v4, v6, and v7, and then I connect these corresponding circles to check 1 and c1. So this graph is sometimes called a factor graph, or it is called a Tanner graph of a code. So, so here is an important class of graphs that define low density parity check codes. These graphs are sparse, so there are no many connections between variables and checks. So in this case, you see each variable has a degree 3. It is connected to 3 checks, and each check here has a degree 5. It is connected to 5 variables. So, so obviously this number of connection is much small. You can also see that this number of connections with the out degrees of all these checks is the same, and out degree of all variables here is all the same. It is 3 and 5 here. So here is the set of variable nodes and set of check nodes, and there is small number of edges compared to number of variables or checks. So this is why we call the graph dense, sparse. So it is, if I write parity check matrix that corresponds to this graph, it will have small number of ones. It will actually have 3 ones in each column, because remember, columns corresponds to variables, and it will have 5 ones in each row, because checks corresponds to rows. So this is what we describe by I already described this. So I described our degree of variables and our degree of check nodes. It is a number of neighbors of variable nodes and number of neighbors in the check nodes. In our case, in our example, it was 3 and 5. So this dv is a degree of a variable node, and it is 3. And this c is a degree of a check node, that is 5. So this d doesn't have to do anything with the minimum distance notation that we used before. So, and these are our definitions. So we say that a vector v is a code word if and only if for each check node the modulo 2 sum of its neighbors is equal to 0. And we consider this class of regular LDPC codes, and we denote it by n, gamma, and rho. So as a Tanner graph with n variable nodes, so that the degree of each variable is gamma, and each check has degree rho, and there are m of these check nodes. So the rate of the code is k over n, and this rate is bounded by this ratio of variable degree and rho degree. We are not going to go into details how this can be derived. So if I give you a parity check matrix, you should be able to define a Tanner graph. But Tanner graph is not uniquely defined by the code. It is defined by a given parity check matrix. So here is one example of our regular code with 25 variable nodes and with our degrees of variable nodes of 3 and 5. So here is a question. course, it takes some time to verify, but hopefully you guessed it correctly. Maybe, Brian, you can call the poll. It's not easy to do it very quickly, I understand.
Bane, maybe meanwhile there's a question on in the Q&A. Maybe I thought you can answer it live. So Marco Raffini asks, what role does the assumption of noise statistics play in the design and performance of a code?
So far we show that for binary symmetric channel, what we need to find is a code word closest to a received word, and obviously this closeness is derived through this Hamming distance. And remember how in the Hamming we derived. Our goal would be always to maximize this a posteriori probability that we described earlier. So, but depending on the channel model, this derivation can be different, and what we need to optimize could be different. So, for example, in Gaussian channel, if the channel is Gaussian, what we can show that what we need to find is a code word that is closest to a received word, but not in Hamming sense, but in Euclidean sense. This would be a code word that is closed in Euclidean way through a code word. And similarly for other type of channels, this distance can be defined differently. Okay, so maybe I move to the next question. This can be, you can verify the correct answer is B. And you, of course, verify this by drawing connection between checks and variable nodes as we described. Okay, so let me skip this question. So let's say now I want to design a decoder for binary erasure channel, and this decoder needs to operate on this Steiner graph. So what I do is the following. So imagine, remember, our channel doesn't make errors; it can only introduce erasures. So I transmit 0 and 1, and then I receive either 0 or 1 on erasure. So you obviously, these bits that are correct, either 0 and 1, it doesn't matter whether they are 0 or 1. So I will denote them by these black squares. And erased bits, I will denote by white squares. So now I want to define some simple algorithm of recovering these erased bits. So remember, if the bit is involved in a parity check equation, and in this parity check equation, this erased bit is the only erased bit, it can be recovered from the rest of the correct bits. So that's the basic principle. So what I'll do is try to recover these bits in a recursive way. So what I will do is do this. So first, I will do it iteratively. So in the first iteration, I will identify parity check equation that involve only a single erased bit. So these are these parity check equations. And then obviously now these two bits are, this erased bit can be corrected. These other checks are not useful in this case because they involve maybe 2 or more erased bits, and they cannot be used to correct erasures. So then I correct these bits, and then in the next iteration, I again find, so these are obviously these checks that are already used. I'm not going to use them again. And this is again the check that involves a single erased bit. So this bit can be corrected. And the next iteration, this is again I identify check with a single corrected bit, and etc. So you see, by peeling, I can correct more and more erasures. And then finally, all these checks are used, and obviously these 3 checks are never used, but I was able to correct errors. So you see, it is a very nice and promising way to correct errors because the algorithm is simple. It uses the same rule in every step, in every iteration. However, as you can imagine, there could be situations when errors cannot be corrected. So let's illustrate this in this example. If I run the same algorithm, you can see that in this second iteration, there are no white checks. There are no error checks that I can use to correct errors, and therefore I won't be able to recover. So you see, now if you look at this particular configuration, you can ask yourself why this couldn't be corrected. And the answer is that actually these errors were connected to checks, and in this way, that there are no checks, that each check involves 2 or more erased bits. So this configuration describes what is called a stopping set, and the presence of these stopping sets obviously are bad for this decoder. And when we design codes, we need to design graphs. We need to design parity-check matrices to avoid these configurations. So the situation is a little more complicated when we work in the binary symmetric channel. So for binary symmetric channel, I will describe intuitively one decoding algorithm that we'll call Gallagher-B algorithm. And remember, we transmit bits. Some of these bits are flipped, and we compute parity checks. So what this algorithm does, it defines rules to transmit messages between variable nodes and check nodes. So the algorithm will be done by message passing. So the algorithm will propagate messages between variable nodes and check nodes according to some rule. So these are variable nodes, and these are neighboring check nodes, and this is check node and variable node. So you know the message will be always sent between neighboring nodes, between neighboring variable nodes and check nodes. So imagine now that this 0 represent 0, the white represents 0, and 1, and red represents bit 1. So this actually means that the check node is sending values 1 to this variable node. So this 1 means that this check is not satisfied, that it is the corresponding value of the syndrome is not 0. So here is the rule that is used. So we send when there is majority of messages, we send majority value. So there are 3 red messages so there are 3. So the message that I send to this check node is based on messages that are obtained from all other variable nodes except all these other check nodes except this check node, and it is majority of these messages. So there are 3 reds, and 1 and 1 white, and therefore I send a red message. If there is a tie, and as in this case, I just send 0 value. Similarly, for the check node, the rule is the following. I send XOR of all messages. So here I have 2 1s, and this red value is also 1. So it will be 3 1s. So I send 1 plus 1 plus 1, which is 1, XOR, right? So I will be sending 1 red message. So the rule is that what check node does is make the number of red messages even, red messages even, red arrows. And the decision is made for a variable node is made on as a majority of all incoming messages. Okay, so these are simple rules that we will describe. And now I want to see how errors are corrected. So imagine that I have this graph, and let's suppose that there are these three errors, and these two nodes are white. So these white nodes are correct, and red nodes are in error. So you see, if I computed the check values, you will see that all these checks are going to be 1. So the check equations are not satisfied. And now what I do is the following. So in the first iteration, all variable nodes are going to send 0 value, because 0 values are most likely thing to be error, right? So the error typically will have small number of non-zero elements. So all values will be 0. And these values are sent to check nodes. So now remember the rule of the check node that it will do XOR of all incoming messages. But in our case, there is just one incoming message. So it will be XORed with this red value. So, so 1 will be sent. So all check nodes actually send value 1 to all variable nodes. So now all variable nodes can do a decision. Decision is based on majority of all incoming messages, but all incoming messages are 1, as you can see, red. So decisions are made to be 1. So all these bits are considered to be 1. And you remember that this was incorrect. What actually happened is that there are just errors in these positions. So obviously the syndrome is not matched. So the syndrome that I calculated has 1, 1, and 1, and it should have all ones in all these values. So therefore, the error is not found. So I need to continue it in iteration. So in the next iteration, I remember messages that were sent to variable nodes. So now each variable node sends majority, as you remember. Okay. So and you know, in the next iteration, you see the messages that are sent in the next iterations are majority. And finally, again, in the second iteration, I have again syndrome mismatch. And messages sent to variable nodes in the previous iterations is this. So, and you see when I continue sending messages as before, the messages sent in the third iteration will be the same as messages that are sent in the first iteration, which is all 1. And therefore, you see that the decoder couldn't correct errors. So this problem that actually I know that Narayanan you need to continue with the quantum part. So I just want to make.
Bane, I think it's fine if you take another 5 to 10 minutes. I think I should still have time. So please feel. I think there's enough time for you to go through the rest of the slides, so you don't have to speed up. Okay.
So let me summarize what we have so far from decoding. So we had one example where we have just erasures. So we have a system of linear equations, and then if one equation contains just one erasure, it can be recovered. And we show that we can do this iterative in a recursive way. So we slowly correct one erasure after another. Then the second rule that we describe is this message passing, where we do the following. So we consider variable nodes and check nodes, and we define these messages as majority or XOR. So our goal of a decoder was to match the syndrome. Let's say we observe some syndrome and I want to match it. So the way that I want to match the syndrome is to find error pattern. And error pattern I try to find by propagating messages. So this and the update rule was actually very simple. Every time variable node sends to a check node sends majority, and every time a check node to a variable node sends XOR of all incoming messages except this variable. So now, can we generalize this rule? Can we find, and we show that this method is actually pretty simple, and it can scale and can be correct a lot of errors if these errors are somehow not grouped. But is there some still simple but more powerful algorithm than this Gallagher-B algorithm? So the answer is that there are a variety of algorithms, and our lab has been working on these algorithms for many years. So we understand these algorithms very well, and they can be described by modifications of approximation of what is called belief propagation algorithm. So I realize that I don't have time to derive belief propagation, but at least I can give you an intuition about how belief propagation algorithm works. So the best, the way to make an analogy is to think of a crossword puzzle and think of how you correct a crossword puzzle when you have errors or when you have incomplete knowledge. So remember, you are supposed to put right letters, but you don't have, and you are doing this by looking at clues across and down. And then as you are writing letters, more and more you are sure about the correct letters, you are writing this on the paper by the pen, and you make the letter bolder and bolder. I know that new generation don't use pen and pencil anymore, and you use, I don't know, maybe crossword puzzles in electronic form, but this analogy uses analog information, this kind of confidence, your confidence about a letter in a certain bit. So this is what belief propagation tries to do. It tries to increase the belief or confidence of a bit that you want to decode. So the way that you do is the following. So I'm going to give you one intuitive way of doing it. So imagine, so let's say that I want to compute message that is sent from a variable node to a check node. So So let's suppose these are beliefs or confidences or likelihoods that correspond to these edges. So these likelihoods or beliefs are beliefs about a variable node that is obtained from these check nodes. So you can think of these numbers to be positive or negative numbers, and let's say high positive numbers can correspond to beliefs, high beliefs that this bit is 0, and high negative numbers can represent beliefs that this bit is 1. Obviously, smaller beliefs are represent uncertainty about this bit. So what you can do is construct a very simple rule where every variable node sends a sum of these beliefs to a check node. So it sums its beliefs plus its a priori beliefs of a variable node. So this a priori belief is lambda, and this is the sum of incoming belief. So now the check node, what the check node does is it obviously needs to ensure that these are the parity check, that it is satisfied. So the check node actually does the following: it sends the minimum belief of incoming messages, but with a correct sign. And this correct sign is obtained as a product of signs. So remember, negative messages correspond to ones, positive messages correspond to 0. And therefore, since the parity check equation needs to be satisfied, the product of signs must be 0. So this describes what is called mean-sum approximation of a more complicated algorithm called belief propagation. And these algorithms and variants of this algorithm are now built, are implemented in many communication systems. So now I will skip this derivation and tell you a list of applications where low-density parity check codes and iterative decoders, including these mean-sum algorithms, are used. So these are wireless communication, satellite communication, disk-based communications and also hard drives and flash memories, and they're all included in the standards of variety of classical standards. So now what the reason that we spend a lot of time in covering low-density parity check codes is that they are also identified as a good and promising candidates for quantum error correction. And now Narayanan will describe concept of quantum error correction and tell you how these codes are connected to quantum codes and how decoding algorithms can be constructed. So I guess, Narayanan, I can start and share the slides.
Yeah, and then I'll start sharing.
Yes, except that now I need to figure out how I do it. Okay.
Give me 1 second. Do you see my slides?
Yes.
Okay, thanks, Bane, for the nice introduction to classical error correction codes. I hope everyone is on board with and has a good idea of how we correct errors in classical communication systems or data storage devices and so on, where everything is in bits and all the computation we do are modulo 2. And now you hopefully got the rhythm of how error correction works. So the basic idea is to add redundancy to your data and then use that extra redundancy to detect errors using the tool of syndromes, and then use the syndrome to then run a decoder that tries to estimate what error is most likely to have happened. And that can use domain knowledge, that can use specific knowledge of the noise characteristics, and so on and so forth. And there's a lot of considerations, but we didn't delve deep into these considerations here, but hopefully you got the main ideas of how error correction works. So now we move on to the quantum part of this course. So broadly, this is split into 3 parts. So we will spend quite a bit of time in discussing the fundamentals of quantum information and quantum computing, like what are qubits, what are quantum gates, and so on, because I think these are important to understand how error correction is implemented later. So we will spend quite a bit of time in discussing the fundamentals. And then we will move on to discuss something called the stabilizer formalism, which I think is quite important and useful even beyond error correction. So we will spend quite a bit of time there, and then that will naturally lead us to quantum error correction. So we won't discuss a lot of advanced topics in quantum error correction today, but we will cover enough basics so that you feel knowledgeable to go and read papers and try and understand what they're doing. Okay, without further ado, let me get into this. So as you might have learned in the past few days of different short courses in this winter school, there are different companies and different academic groups trying to build quantum networks, quantum computers, and so on. I've just listed some of the key ones here. Yeah, so I've just listed some of the key ones here. So Google and IBM, for example, are using superconducting circuits as to build qubits. So these are man-made qubits, and then they have to wire them up and then use a dilution refrigerator and so on to build a quantum chip. Whereas IonQ and Quantinium, for example, are trying to trap ions in vacuum and then shine lasers on them to manipulate these qubits, and then manipulate the stored information and do information processing. And then there are other neutral atoms. There are photonic quantum information processing architectures and so on. But all of these are built upon the same fundamental mathematical descriptions. And today we will just focus on this mathematical description and try to get some intuition for how error correction can be made to work in the quantum case. So let's start with the basics. So you might have seen this earlier in the other short courses, but I thought it's good to repeat these things and so that we are on the same page. So a single qubit is like the basic information system in quantum information, or at least in discrete quantum information, where a single qubit state is written as a linear combination of these two basis vectors. So a single qubit is represented by length 2 vectors with complex entries, which means there are linear combinations of these two basis vectors, which we call ket0 and ket1. This is the Dirac notation. And for reasons that will become clear shortly, the absolute value of alpha squared plus absolute value of beta squared should be 1. And so this is the normalization constraint. So in the vector space language, it just means that any single qubit state is a norm 1 vector in the complex vector space of length 2. So there is a nice intuitive visualization of a single qubit on the so-called block sphere. So we draw a sphere. These axes different certain things that we'll see later, but for now let's label different points on these axes. So 0 and 1. So this is not a proper coordinate system. So just for visual purposes, we have 0 marked on the top and ket1 marked on the bottom, and we will see other states showing up in the next slide. And then we can actually visualize the change of a single qubit state as rotations on this block sphere. So now we have just changed the basis. So in the previous slide we were in the 0-1 basis, which is called the computational basis. Now here we have moved on to the so-called sign basis or the conjugate basis. So this is read as ket plus and ket minus. And so ket plus is a linear combination of the two basis states, 0 and 1. So for example, if you take psi, it is alpha 0 plus beta 1. But if you take psi as to be plus, then alpha and beta are both 1 over root 2. And so 0 plus 1 over root 2 is exactly plus, and 0 minus 1 over root 2 is exactly ket minus. So this is the ket plus state and ket minus state. It just means that you have rotated the, so you have just changed the basis on the sphere. So for example, here we have now marked the plus and minus states as well as the two ends of this horizontal axis. So any single qubit state psi can be equivalently represented in any of these bases. And we just picked these two because these are kind of the canonical bases, but you can as well work with any other basis that is convenient to you. Okay. Now we have defined what a single qubit is. It's just a length 2 vector with complex entries that is normalized. Now, how can you change the state of a qubit? So you have stored some kind of information in these complex numbers. Now, what can you do to these qubits? So broadly speaking, quantum mechanics allows us to do two things. One is unitary operations, which are basically complex rotations and are reversible operations. So these are defined or determined by a unitary matrix. So on a single qubit, you have a unitary matrix, which is a 2x2 matrix that satisfies the property that the Hermitian transpose of the matrix is the same as the inverse. In other words, U dagger times U or U times U dagger will be identity. And I'm sure you have seen this before in your linear algebra courses. So that's what a unitary means. So unitary operations of rotation. So you can take this psi vector, and if you apply U, it just keeps rotating on this block sphere. The other thing you can do is measurement. So measurement is our only way to actually learn something about the system, because unless you measure the system, you cannot retrieve any information from the quantum system. And so for measurement projects the state on a basis, and it's irreversible. So for example, if you start with alpha 0 plus beta 1, like here, and when you do a measurement, it projects onto one of these basis states, as we will see shortly. And similarly, depending on which basis you measure, the collapse changes. And this process is irreversible. So we have two broad processes, unitary evolutions and measurements. One is reversible, the other is not. So this is about a single qubit system. And now let's get deeper into each of these kind of operations. So first, we consider unitary operations. So the first quantum operation, the unitary operation that we will see, is called the Hadamard. So the Hadamard is kind of widely used even in classical communication. So you might already be familiar with this matrix representation of the Hadamard. The Hadamard, you can check, is unitary. So what it does is it actually changes between the two bases. It switches between the computational and the conjugate basis. So if you start with the 0 state, and if you apply Hadamard, it rotates the 0 and it gives you a plus state. And similarly, if you start with 1, it rotates to give you the minus state. Similarly, if you start with plus, then if you do Hadamard, it rotates it back to 0. And similarly, the minus rotates back to 1. So you can see that if you apply Hadamard twice, you get back to the same state. So this is the matrix representation. And let's see visually what the Hadamard is doing. So for example, we are starting with this red arrow, which points to the plus state. Okay, so this point is the plus state. And what the Hadamard does is you take the initial state, then you rotate 90 degrees by the y-axis. So here we have labeled the axis X, Y, and Z. So now you rotate 90 degrees by the y-axis. Now it points down. And then you rotate 180 degrees about the x-axis. So the x-axis is the horizontal axis. And from here, you go back to here. And this we have already seen is the 0 state. So what we have just seen is the Hadamard takes the plus, which is here, to the 0, which is there. So here's the first poll question. So if you start with the single qubit state 0 and you apply the Hadamard gate twice, what is the resulting state? So we can close the poll now. Hope everyone got the answer. Okay, perfect. So you start with 0 and Hadamard is its own inverse. So if you apply it twice, you get back to 0. Perfect. Okay, so let's keep moving. So we have our first operation was the Hadamard. Now let's see what's the so-called Pauli matrices or the Pauli rotations. These are very important. They play a very crucial role in quantum information and computing. And so let's take some time to understand this. So the single qubit Pauli matrices there are 4 of them, and complex. You can take any of these matrices and multiply by I, or powers of I, which is the I is the imaginary unit, and there are 4 different possible powers of I. So you can multiply any of this by different powers of I, and that's also valid. So these are the Pauli matrices, but the standard representation is I, X, Z, and Y. So to understand these operations better, let's focus on Z. So the Z matrix can actually be written as a rotation about the Z axis on the block sphere. And it's actually a pi rotation. So a rotation by theta is given by this operator. So you can take matrices, and once you have the diagonalization of the matrix, so here Z is automatically diagonal. So if you exponentiate the Z, this is what you get. And up to a global phase, this is equivalent to the poly Z matrix when you take theta equals pi. So this is why the Z operation, the poly Z rotation, is actually a pi rotation about the Z axis. So for example, if you take the plus state and if you rotate pi by the Z axis, what you get is minus. And similarly, if you take the minus and you rotate again by pi, you get back to plus. So this poly Z rotation is basically a pi rotation by the Z axis. And similarly, the X rotation will be a pi rotation by the X axis, and Y will be a pi rotation by the Y axis, where you just change Z to X and Y in those cases. So another thing important is that global phases don't matter. So that's why we were able to drop this extra phase when we took the exponentiation of the Z, and then we showed that it's equivalent to Z. And similarly, you can do this for different angles theta, and all of those can be represented on the block sphere. Now, so clearly what we have just seen, we can apply it to the standard computational basis states. So if you take the ket 0 state and you apply X, it flips it actually to 1. So you can just do this simple matrix vector multiplication. So you have X here, and then you are multiplying it by 1, 0. Remember, these are all interpreted as complex matrices. Whereas in the earlier part of the course, we were working with binary matrices, so everything was modulo 2 or XORs. Here we are working with complex numbers and complex matrices, so you can just do your regular multiplication. There is no modulo. So if you just do X times 1, 0, you get 0, 1, which is exactly the 1 state. And similarly, if you apply X to 1, you'll get back 0. So X just flips the 0 and 1. Similarly, Z acting on 0 does nothing, whereas Z acting on 1 picks up this extra phase of -1. And this is why you can think of X as the bit flip operation and Z as the phase flip operation. And Y you can check is actually a product of X and Z together with an I. And so Y is typically called the bit phase flip because it does both at a time. And so all of these names are given with respect to the standard basis. Now, I mean, you can also change the basis. So what happens if you do the same thing in the plus minus or the sign basis? What happens is Z actually flips plus to minus and minus to plus, whereas X, keeps plus unchanged and picks up a -1 for my ket minus. So this basically means that in the sign basis, Z is actually the bit flip operator, and X is actually the phase flip. But typically these names are given with respect to the computational basis. So we will continue to call X as the bit flip and Z as the phase flip. Okay, so now we have seen that you can do the Hadamard operation, and then you can do these poly rotations. But how can you implement it? But we saw earlier that quantum mechanics allows us to do arbitrary unitary operations, right? So, but unitary matrices are just complex 2x2 matrices, which means there are infinite possibilities. So how do you implement an arbitrary unitary operation? So if you're familiar with classical computing, which probably most of you are, then we know that any logic circuit, any binary Boolean logic circuit for classical computers can be constructed simply from NAND and NOR gates. So the question is, in quantum computing or quantum information, is there a finite but universal gate set? Meaning, can we decompose any unitary operation as a combination of some finite set of operations that we can do in the lab? And turns out that's true. So here is the universal gate set for 1 qubit. So you have already seen the single qubit poly matrices, I, X, Z, and Y. We have seen the Hadamard H. Now we introduce a new gate, which is called the T gate. This is actually a pi/4 rotation. So you can simply, again, do the same exponentiation that we did before, where we took theta as pi/4. And then you get this matrix representation. So it's It's a diagonal matrix, just like Z. But this value is, instead of -1, which is e to the I pi, you have e to the I pi over 4. And this also can be represented on the block sphere as a rotation about the Z-axis by the angle pi over 4. So this is the new gate that you want to get universality. So any unitary operation on a single qubit can be written as a combination of polymatrices, Hadamard, and the T-gate. But I should caution that when you express any unitary as a combination of this, there might be some small error. So you can keep reducing the error arbitrarily by picking better and better combinations. But this is a mathematical result that says that you can represent any unitary arbitrarily well by a combination of these gates. And this might not be exact, but it's arbitrarily close. Now at the end, I've just shown you how to get back, these familiar matrices from the T and Hadamard. So for example, if you exponentiate T 4 times, you get back your poly Z. And if you conjugate, so if you just sandwich the Z between Hadamards, you get X. So you can exponentiate T, get a Z, and then using the Hadamard, you can get X. And then Y is just a combination of X and Z. So I've just quickly shown you how you can put together these operations. So here is the next poll question. So we just defined the T-gate. So can you use the definition to find what is the matrix representation of the so-called phase gate, which is defined as square root of Z or the square of T? Okay, let's see the results of the poll. Perfect. So if you just take T and square it, you had e to the I pi over 4. So when you square it, you get e to the I pi over 2, which is exactly I. So the D is the right option. So most people got it right. Okay, let's continue. Okay, so now we have seen what a single qubit is. We have seen how to do unitaries on a single qubit. Now let's look at measurements on a single qubit. So we are only going to talk about projective measurements in this short course. But if you take any textbook for quantum information, they will also talk about more generalized measurements, but we will not get into that today. So projective measurements are very important, and this is what we frequently implement in practice. So for example, let's say you have the initial state psi, so which is alpha 0 plus beta 1. Now, we call this ket psi. So this direct notation is called ket. Now, if you take the conjugate transpose or the Hermitian transpose of psi, this is denoted as bra psi. So this is the conjugate transpose of ket psi. Okay, so with that notation in mind, let's see what a measurement involves. The first thing you need to do is you have to diagonalize whatever observable that you're going to measure. So here we say that we are going to measure Z. So we first take Z and then write the eigen decomposition or diagonalize Z. And as you might have already noticed, the eigenvectors of Z are ket 0 and ket 1. This is why when Z acted on ket 0, you got a +1 times ket 0. When Z acted on ket -1, you got a -1 times ket 1. Because this is precisely because these are eigenvectors of Z. So you first diagonalize the observable, then you define the projectors using the eigenvectors. So here you have two eigenvectors, ket 0 and ket 1. You take each one to define an outer product. So remember, this is a column vector and this is a row vector. So this is an outer product. So this is a 2 by 2 matrix. Similarly, this is another 2 by 2 matrix. And you can verify that these are projectors, meaning that if you square this matrix, you get back the same matrix. Okay, so you first diagonalize the observable, then you define projectors, and then the possible outcomes are exactly the eigenvalues of the matrix. So the eigenvalues here are +1 and -1. So those are the possible outcomes. So this is what you see in the lab. So when you measure in the lab, you will actually get results +1 or -1. And the probability of each measurement is given by this inner product. So remember, this brass eye is a row vector. You have a 2 by 2 matrix, and this is a length 2 column vector. And so you can verify that the inner product is mod alpha squared, and this is mod beta squared. And this is exactly why in the first slide for a qubit, we said that these two quantities should sum to 1. Because when you measure, you only have two possibilities, and the probabilities of the different possibilities need to sum to 1. And so that's why we defined before. Is there anything on the Q&A that I should answer?
No, I think it is all good.
Okay. Yeah, let me know if I should answer anything, and then I'll answer. Okay, so so these are the probabilities, and now you can go ahead and measure. So for example, and so when you start with the state psi, and after you have defined all of this, you measure in the lab, and the measurement causes outcomes +1 or -1 with these probabilities, and that's just by nature. But after you have seen the measurement result, you can be sure that the state has changed to one of these two possible states. So if you got a +1 result, your new state is psi plus, which is basically m + 1 acting on ket psi normalized by square root of the probability. And you can verify that in this case, that will be ket 0. Similarly, if you got a -1 result, the post-measurement state will be ket 1. And so this is the prescription that quantum mechanics gives us for how to understand a projective measurement of a quantum state, how to measure an observable on a quantum state. So in the block sphere, we have just shown that you start with the state psi, and with probability mod alpha squared, it will project to 0. And similarly, with probability mod beta squared, it will project to 1. Okay, so now we have seen unitary operations and measurements. Now let's take a moment to appreciate what's happening. So you had this single qubit state, and it was normalized, and we have just seen what the reason is. So technically, alpha and beta can be any complex numbers, which means they have infinite possible choices. And so a qubit can technically store an infinite amount of information, but no measurement can retrieve that exactly, because when you measure, the state is going to collapse to 0 or 1. So you cannot just read off alpha and beta just by measuring the state. And this is true not just for this basis, but any basis you measure, any observable you measure, the measurement can only retrieve a finite amount of information. And this is why just a single qubit is not enough. And this is why you have to sort of engineer these unitaries and measurements in a careful way to get useful results through a quantum algorithm. Okay, so we have just seen projective measurement where we measure z. Now I've just repeated the same thing for measuring x, which is another observable. In this case, the eigenvectors turn out to be ket plus and ket minus with the same eigenvalues. So we again define projectors. You have these different possible outcomes and the different probabilities. And for example, if you start with the state psi here, it will project to state plus with probability mod gamma squared. And so hopefully you get the idea of how to calculate what happens when you do a measurement. Okay, so now we have seen unitaries and we have seen measurements on a single qubit.
May I interject? Maybe you can specify in the block sphere if the x, y, z axis there was a question basically, or comment, if they correspond to the x, y, z operators, the poly operators in the basis axis basis.
No, so it was deliberate. So good question. So this was deliberate. So these axis x, y, z actually correspond to the poly x, y, z matrices. But to see the connection precisely, we need to discuss the so-called density matrices in quantum information. But we won't do that today because it's not essential to understand error correction. But if you pick up a textbook on quantum information, you will see the density matrix description of arbitrary quantum states. And then you can actually come back to the block sphere, and then you will see that x, y, z, so the poly x, y, z matrices actually form a basis, so the poly I, X, Z, and Y, these four matrices, actually form an orthonormal basis for orthogonal basis for all 2 by 2 matrices. And so you can take any density matrix, meaning any quantum state, and you can express it as a linear combination of these matrices. And then you can visualize any quantum state on a single qubit as a point in in that case, it becomes a ball. It's not a sphere anymore. But I'm not getting into those details now. But this notation of using capital X, Z, and Y was deliberate. It does refer to the poly matrices. So just to reiterate, when you think of this as pure states on the sphere, it's not a proper coordinate system. But if you go to the density matrix description and then interpret X, Z, and Y as poly matrices, then it is a proper coordinate system. Okay. Okay. So then, so let's just wrap this up with the circuit notation that we will use conveniently later on. So for single qubit gates, we always write circuits that where the time goes from left to right. So the input state is on the left, which is say psi, and then the first operation is say unitary U2, and then the second operation is unitary U1. So when you actually write the output, you have to first apply U2 and then U1. So this will reverse. That's something you just need to keep in mind. So when you read circuits, you go from left to right, but when you want to write it as the output state, you have to go from right to left and then write it in the right order. So hopefully that makes sense. Okay, so we have seen already that the Hadamard poly matrices and the T gate form the universal set. And in fact, you can get the poly matrices just using T and Hadamard. For example, if you apply T twice, you get the phase gate. If you apply the phase gate twice, you get the poly Z. And then if you sandwich the Z between Hadamards, you get X. And then if you put the X and Z together, you get Y. So we have just shown how to get, basically these are kind of like, Legos, right? So you can just put them together to get different unitaries. And similarly, measurements will be represented by this meter symbol, where we will write the observable on the top, and the possible outcomes will be written on the right. And this double line means it's a classical outcome. So it's a classical binary outcome, whereas the input is a quantum state, which is represented using a single line. Good. So with that, let's go ahead with the next poll question. So you have the initial state 0, you apply the Hadamard, that changes the state, that's a unitary operation. And then you measure Z. And then the question is, what is the probability that the result is -1? And what is the corresponding post-measurement state? Okay, let's close the poll. Let's see what the results are. Okay, I think many people got it right. So the answer is A. Let's just see why the answer is A. So what happens when you you start with 0, right? And then we applied Hadamard. That gives you the plus state, which we already saw was a superposition of 0 and 1, with the coefficient being 1/√2. And then you're measuring in the Z basis. And so you will get outcomes, +1 or -1, and each has probability mod alpha squared equals mod beta squared. In this case is 1/√2 squared, which is half, right? So in this case, both alpha and beta are 1/√2, and so the square is half. So the probability is half. And we said that the measurement result is -1, so the outcome is +1. So the ket1 state. And so this is why option A is the right answer. Okay, so let's proceed. Now we have seen how to manipulate single qubits, right? With unitaries and measurement. Let's now go to 2 qubits and just expand to more qubits. So when you move to 2 qubits, the first new operation you want to do is the control NOT, which I'm sure you have heard of multiple times in other courses this week. So the control NOT is nice and simple. So it's kind of like the quantum version of the XOR operation that you might be familiar with in classical computing. So you have 2 qubits, A and B, coming in. So think of A and B as computational basis states. So this A can be 0 or 1, and B can be 0 or 1. So the input is different possible combinations of zeros and ones, ket zeros and ket ones. Now what C0 does is, if the control qubit is 0, it does nothing to the target. So it just adds 0 to the target, which does nothing. But if the control qubit is 1, it flips the target qubit. Right? So this is what the control NOT does. So in classical computing, typically just this part is the XOR, right? So you just send A and B, you get A XOR B. But in quantum, everything has to be reversible. And that's why we also retain one of the inputs, so that from the output, you can also go back to the input. So this is a reversible operation. So it's a unitary operation. And the matrix representation of the C0 is just this. So it's actually block diagonal with identity and the poly X. So if the control qubit is 0, it does nothing. If the control qubit is 1, it applies the poly X, which means it flips the target. So that's why you have the X here. And it turns out that if you want to do arbitrary unitary operations on any number of qubits, say n qubits, then you can always decompose that circuit as a combination of Hadamard and T gates on different qubits and C0s on different pairs of qubits. Of course, the approximation gets better and better if you do the sequence of operations carefully. But it might not always be exactly the unitary operation, but it will be like a little bit away from the unitary in the L2 norm. So if you're familiar with norms of matrices, when we say universal, it means that you can do any unitary, which is a 2 to the n by 2 to the n operation. Matrix can be written as a product of these matrices on different qubits or different pairs of qubits. But the product of the sequence will be close to the target unitary in L2 norm, if that makes sense. Okay, so now to represent mathematically what happens with multiple qubits, we need to understand the Kronecker product. So if you have 2 matrices, A and B, let's say A has dimensions m by n, and B has dimensions p by q. So let's say these 2 are the A and B matrices. Now, when you take the Kronecker product, what happens is you have to take the first entry of the A matrix and then multiply by the full B matrix, right? So you're just blowing up the matrix. So just this single number, A11, gets blown up into a matrix of the size of B. And so this is P by Q. And similarly, you go to the second entry of A, multiply by B, third entry of A, multiply by B, and so on. So once you have done, you have blown up the matrix such that the output matrix has dimensions m times P by n times Q. So m, which is the number of rows in the first matrix, times the number of rows in the second matrix, by the number of columns in the first matrix times the number of columns in the second matrix. So mathematically, this is what the Kronecker product is. But for our purposes, it just suffices to remember this property. So if you have a product of Kronecker products, you have A Kronecker B times C Kronecker D, then you can actually do the corresponding products first. So A times C and B times D, and then take the Kronecker product. So this is a super useful property so that you don't have to do this crazy math in your head all the time. So whenever you're applying matrices to qubits, you can just leverage this property to just apply the corresponding matrices to the corresponding qubits. You will see examples of this shortly. Okay, now let's get back to the same C0. So how do you represent these inputs and outputs? So for example, let's say you start with A and B being 1 and 0. So when we write ket 1, 0, I actually mean ket 1 Kronecker ket 0. So we just collapse this to 1, 0 just for convenience, right? Shorthand notation, if you like. So ket 1, 0 means there's a Kronecker product in between. And you can take the Kronecker product and you will see that you get a new basis vector of length 4. And this basis vector, so this is what the input is, which is 1, 0. And now you apply C naught on 1, 0. You do this matrix vector product, you get the output 0, 0, 0, 1. And that turns out to be a Kronecker product of ket1 with ket1. So what you have done is the input ket1, 0. So the input 1, 0 has transformed into 1, 1. Similarly, if you input 1, 1, you will get back 1, 0. And this truth table exactly tells you how to think of the C naught. When the first input is 0, nothing happens to the second. And the first input is 1, the second bit gets flipped. Okay, now we have the basic pieces to get to something exciting, which is entanglement. So you start with, say, the 0 state, and you apply Hadamard, you get the plus state. You know those now. And then if you can add another qubit, which is, say, in the 0 state. And now using this Kronecker product notation, you can write it. You can just take 0 plus 1 over root 2, Kronecker 0. And then you can use linearity of the Kronecker product to write it at this superposition. So this is superposition. And then you do the C naught between the two qubits, which means this 1, 0 now becomes 1, 1, as you saw on the previous slide. And that's exactly, and this gives you a very interesting state called the Bell state or the EPR pair. And this is an entangled state. What does that mean? It means that you cannot take this Bell state and express it as a tensor product or Kronecker product of two single qubit states. So you cannot decompose this superposition into a Kronecker product of two single qubit superpositions. And this is the mark of entanglement. And the Bell state or the EPR pair is the famous, is one of the basic, but the most famous entangled states. And I'm sure you have heard of the Bell state in other courses as well. And so now you know exactly how to produce entanglement. It's basically a combination of superposition and linearity. In linear algebra terms, that's how you produce entanglement. Okay, so now we have seen single qubits, unitary operations, measurements, multiple qubits, universal gates. Let's now just summarize everything that we have seen now. So the computational basis states on n qubits are given by Kronecker products of computational basis states on single qubits. So each of these VIs is 0 or 1. And if you take a Kronecker product, you get the basis states for bigger and bigger number of qubits. Now, an arbitrary quantum state on n qubits is written as a complex valued linear combination of these basis states, and the norm has to be 1. And unitary operations are 2 to the n by 2 to the n matrices. Remember, these are large matrices. This scales exponentially with the number of qubits. And these are unitary, and that's how unitary evolutions are represented. Finally, when you measure an observable, you take the observable, which is basically a Hermitian matrix. So O is the same as O dagger. And you first diagonalize it, meaning that each of these MIs are orthogonal projectors. These small MIs are the eigenvalues. And the eigenvalues are exactly what you read off in the lab when you measure. And the probability of obtaining a measurement result is given by this inner product. And the state changes. If you start with the state psi, after you do the measurement, the state changes to psi sub I, which is basically the projector applied to the state, normalized by the probability of the outcome. So this summarizes how you can initialize an arbitrary n-qubit state, unitarily evolve the state, and then measure any observable that you want on the state. And this is all the pieces that happens in a quantum system, in a quantum computer or a quantum repeater or quantum network. Okay, so now let's try to use this Kronecker product property that I introduced a couple of slides before. Remember, you have A Kronecker B times C Kronecker D, and just use the property to guess, to calculate what the outcome is. So if some of the notations are not clear, you can always go back in the slides. So the link to the slides were shared in the chat. So you can go back to some of the slides and see what the notations are. Okay, we can close the poll and see the answers. Okay, that's right. So when you so if you use the Kronecker product property, what happens is, this is A Kronecker B times C Kronecker D, which is AC Kronecker, sorry, BD. And so AC is X0, and then BD is Z1, and we have already seen what happens. So X is the bit flip, and Z is the phase flip. And that's exactly option D. Okay, so hopefully that part was clear. All right, so let's keep moving. Okay, so now we have just looked at entanglement. So we looked at bell pairs. So this is the circuit that you would represent to generate bell pairs. So you start with zeros, and then you do Hadamard C0. You get a bell pair here. Now let's measure a bell pair. So let's measure the poly Z on the first qubit of a bell pair. So at this point, you have the bell pair, and now you're measuring Z on the bell pair. So you can do the same thing that I just showed you a couple of slides before. You can write the projectors when you're measuring. So you're measuring only the first qubit. So the second qubit just has identities. And for the first qubit, you have the corresponding projectors. And you see that after you apply these projectors for either of the outcomes, you either get ket 0, 0, which means ket 0 tensor ket 0, or ket 1 Kronecker ket 1, right? So the beautiful thing here is that after the first qubit is measured, you have a particular output state, and the second qubit also collapses to the same state. So this is a high amount of correlation that is beyond what you can achieve classically, and that's the sign of entanglement. And this is true not just for this particular Bell state 0, 0 plus 1, 1, but for these other variants of the Bell state. So this is called the Bell basis, meaning that on 2 qubits, these 4 possible states form an orthogonal basis for all 2 qubit states. And so the Bell basis is an important basis in which measurements are also done. So for example, the Bell state measurement is a common operation that's done in quantum repeaters. Okay, so the sign of entanglement is that the outcome of the result of measuring 1 qubit of the entangled state is highly correlated with the outcome of the other. Okay, so you can take these Bell basis states, and you can check that these are eigenvectors of the following operators. So we have already seen that 0 and 1 are the eigenvectors of Z, and plus and minus are the eigenvectors of X. And here we are checking what operators for which these Bell states are eigenvectors of. So for example, if you take Z Kronecker Z tensor Z, which I'm representing here as ZA ZB on qubits A and B, then if you just apply Z Kronecker Z, you apply the Kronecker product property, and then you apply the action of Z on 0 and Z on 1, then you see that you start with the phi plus state or phi minus state, and you end up with the same state. Right, so the phi plus minus states are +1 eigenvalue eigenstates of Z Kronecker Z. Similarly, if you take the psi plus minus states, you do the same kind of math, you end up seeing an extra minus sign out, which means that psi plus minus, which means these two states are -1 eigenvalue eigenstates, eigenvectors of the matrix Z Kronecker Z. And similarly, you can do the same kind of exercise using X Kronecker X or minus Y Kronecker Y, and you will see that these are eigenvectors. So to put everything together, you have these Bell basis states and the so-called stabilizers, which means these operators stabilize the vectors. That means that these vectors are +1 eigenstates of these signed operators. So Z Kronecker Z, these two are +1 eigenvectors. And for if you take plus X Kronecker X, then phi plus will be a +1 eigenstate. Similarly, if you take minus X Kronecker X, phi minus will be a +1 eigenstate. And similarly here, you fix the sign of Z Kronecker Z as minus. And again, if you apply plus here, the psi plus state will be a +1 eigenstate. And if you take a minus here, the psi minus state will be a +1 eigenstate. So that's what we mean by stabilizers. Stabilizers mean that the corresponding state is a +1 eigenvalue eigenstate of the operator. That's what we mean by stabilizers of a particular state. Okay, so now we have, here we have these 2-qubit states, and there can be multiple stabilizers, and for 2 qubits, you will have 2 independent stabilizers, and then you can also take products of that. So you'll have, in this case, 4 combinations of this. And so the elements of the stabilizer must mutually commute. So what do I mean by commute? For example, if we take x and z, then they anti-commute. So xz is actually minus zx. But if you have x Kronecker x and z Kronecker z, and then you do the same kind of multiplication, then by using the Kronecker product property, you can verify that x Kronecker x and z Kronecker z commute, meaning that you won't get a minus sign, because you get a minus sign twice, and then that squares to 1. So elements of a stabilizer must mutually commute. And once, if you can do that, then linear algebra tells us that you can simultaneously diagonalize these stabilizers. And that's when you have the same set of eigenvectors for all these different stabilizer elements. So this is just coming directly from linear algebra, which tells us that commuting matrices can be simultaneously diagonalized. And here we have these commuting stabilizers, and that's why they have a common eigenbasis. So these vectors, these Bell basis states, are common eigenvectors of all of these stabilizers. So you can generalize this. So this was for 2-qubit states, but for n-qubit stabilizer states, you will have n poly stabilizer generators, meaning that n independent generators, but you can always take combinations of them. So you will overall have 2 to the n stabilizers, poly stabilizers. So this is a very important slide. So let's take a moment to make sure that this sinks in. So we have defined the Bell basis states. I've introduced the notion of stabilizers. So which means, in this case, it means that these states are +1 eigenvalue eigenvectors of these signed stabilizers. And these stabilizers must commute, and commutativity can be checked by using the poly commutation rules and using, of course, the Kronecker product property. So this is what we mean by stabilizer states. So those states that have poly stabilizers are called stabilizer states. Okay, now we can go from 2 qubits to 3 qubits, and then we end up with the so-called Greenberger-Horn-Zerringer, or the GHZ state. So the standard GHZ state is just 0, 0, 0 plus 1, 1, 1. And for this particular state, the stabilizers are Z Kronecker, Z Kronecker I Kronecker, Z Kronecker Z, and X Kronecker, X Kronecker X. But there can also be variants of these GHZ state, and there are 7 other variants. And those are stabilized correspondingly by changing the combinations of signs here. So you have 2 possible signs for each generator. And so there are 8 possible states. One of them is here, which is the standard GHZ state, but the other states can be obtained by flipping the signs. And this is just a natural extension of the Bell states to 3 qubits and beyond. Okay, so I just want to make sure that you got the idea of stabilizers. So let's go ahead and do this problem. So you're given this particular variant of a GHZ state, and I would like you to check which of these options correspond to the stabilizers of the state.
Narayanan, there's a question on
Yeah.
how important stabilizers are. Maybe you can answer that live since you have a break.
Sure. So stabilizers are very important, I would say, especially for error correction purposes. Stabilizers are the way where we are going to construct these quantum parity checks. So classically, you saw the parity check matrix, the H matrix, which was basically checking different combinations of bits of the code word summing to 0, right? Similarly, for quantum parity checks, you will see that stabilizers are our way to go. So the stabilizers will become the parity checks. So stabilizers are very important. And even outside error correction, stabilizers are important even if you're thinking of simulating a quantum computer, right? So how powerful is a quantum computer? And when does it go beyond the reach of a classical computer? So this is the problem of classically simulating quantum computers. And so there is this famous theorem called the Gottesman-Nil theorem, which I will briefly state shortly, which tells us that there are a set of states and operations in quantum information that can be efficiently simulated by our laptop. You don't need a quantum computer to actually evolve and manipulate those states with those operations. So that kind of marks the boundary of what is beyond the reach of classical computers. And so in that sense, the concept of stabilizers is very useful to think about. And another use that I'll show later in the stabilizer formalism is you can actually track some of these states through some of these circuits by just manipulating the stabilizers rather than storing the whole vector, which is exponentially large. And you will see that you'll see all of that shortly. But great question. Okay, so let's close the poll and see if people got it right. Okay, so there's a tie between A and C. So basically what you want to check is you apply these matrices to the state and see if you get a +1 result. So let's take, for example, Z tensor I. And if you apply it to 0, 0, 1, what do you get? So let's do this quickly. So you take ZZI, you apply it to 0, 0, 1. What do you get? So Z acting on 0 is 0. And then Z acting on 0 is 0, I acting on 1 is 1. So you get back 0, 0, 1. So ZZI seems fine, right? Similarly, you want to check IZZ acting on 0, 0, 1. What do you get? You get 0. Z acting on 0 is 0. But Z acting on 1 gives a -1. Right? So you pick up a -1 here. But what I asked for was stabilizers, which means that you're only supposed to get a plus sign out. Right? So that's an indication that the sign for the second operator should be minus. So C could be an option. But you also want to check XXX. So what happens when you do XXX on 0, 0, 1? You get 1, 1, 0. Right? You just flip all the bits. And so 0, 0, 1 becomes 1, 1, 0, and 1, 1, 0 becomes 0, 0, 1. So XXX seems fine. So only the IZZ needs a -1, and so C is the right option. All right, so let's proceed. So hopefully that gave you an idea of how to think of stabilizers and how to do these calculations using the Kronecker product property. Okay, now we get into the stabilizer formalism. So we are exactly getting into the question that was just asked. So we had this Bell state generator circuit. It was quite simple. You can just write down these states as length 4 vectors. Now let's go to a slightly larger circuit. So you're starting with the state 0, 0, 0. You're applying these combinations of Hadamards and C-naughts. Remember that this C-naught means this is the control, this is the target. Whereas for this C-naught, this is the control, this is the target. And the question is, what is the output state? Right? Of course, you can go ahead and do the math. So you have the matrix representation for Hadamard, C-naught, and everything. So you can put together, maybe a MATLAB code or something like that, and just, do all these matrix vector products and get the output state. But you see that as the number of qubits gets larger and larger, the size is growing exponentially because the vectors grow exponentially in length. These are length 2 to the n vectors. And this is not very easy to think about. And you don't want to think about it as matrices and vectors in this way. And this is why we need the stabilizer formalism. And so before we get into how the formalism works, an important class of quantum operations are called the Clifford gates. So what are the Clifford gates? So here is the definition of Clifford. It just says that if you take any polymatrix, so a unitary operation U is called Clifford if it maps polys to polys under conjugation. So this operation here is called conjugation, where you sandwich a Pauli matrix in between the matrix U and its Hermitian transpose U dagger. So when you do U dagger to any Pauli matrix, if you get only another Pauli matrix as an output, then U is Clifford. Otherwise, it's not. Even if it fails for one Pauli matrix E, it's not Clifford. And Pauli matrices we have already defined. It's just tensor products or Kronecker products of the single qubit Pauli matrices along with some faces, right? So these are called Clifford gates. And conveniently, the Clifford gates can be, any Clifford gate can be generated as a combination of Hadamard, phase, and CNOT. So remember, phase was the square of T. And so the only difference between Clifford and universal computation is this extra gate T, which is square root of P. And so if you just change the P to T, you get the universality. If you only have the P, you can only do Cliffords. And so it's a nice delineation of Cliffords and non-Cliffords. So typically the universal gate set that people talk about in quantum computing or quantum networking is the typical gate set is called the Clifford plus T gate set, meaning you have the Clifford gates, but you also have the T gate. And with this, you can arbitrarily approximate any unitary operation that you want. Okay. Now, for Clifford gates, you can actually track the state very easily. So here's how you do it. So you want to understand how Cliffords conjugate Pauli matrices, right? So that's basically what we're interested in. So you know that if you take a Pauli matrix E, you conjugate by a Clifford, you should get another Pauli matrix E prime. Now, conjugation can be thought of in another way just by pushing this U dagger to the other side. So if you push the U dagger to the other side, what this equality is saying is that if you have a state here, let's say you're acting this on psi, it states that first applying the Pauli E and then the Clifford U is the same as first applying the Clifford U and then the Pauli E prime, right? So you have just evolved the Pauli E through the Clifford, and that just swaps the order of operations. So let's see some examples of this. So for example, if you take the phase gate, first applying Z and then the phase gate is the same as doing the reverse. Because both of them are diagonal, they actually commute. But if you take the X and then the phase gate, that's equivalent to first doing the phase gate and then the Y. Similarly, for Hadamard, first doing X and then Hadamard is the same as first Hadamard and then Z. So these are basically different, sort of Pauli tracking, kind of cheat sheet, if you want. And similarly, there's a cheat sheet for CNOTs as well. So if you have an X at the input of a CNOT and then the CNOT, you can as well do the CNOT first and then the X's on both control and target. Similarly, if you have an X on the target of the input of a CNOT, then nothing happens if you swap the order. And similarly, there are rules for Z. So this is kind of like a nice cheat sheet. And with this, armed with this cheat sheet, let's try to understand the circuit that we saw earlier, right? So you have these three input states, and you have this circuit, which is all containing only Clifford gates, Hadamard, and CNOTs, and you are interested in the output. So the way you do this efficiently is the following. First of all, you realize that at the input, the Pauli Z stabilizes each of the qubits, right? So Z acting on 0 is 0. We have seen this before. So the stabilizers for the input state are just Kronecker products of Z's on different qubits. And here you have, either identity or Z on each qubit. So you have 8 possible stabilizers, right? And so what you can do is you can use this cheat sheet to track these stabilizers through the circuit to get the stabilizers for the output state. So here is how you do it. So let's first consider Z on the first qubit. That's an input stabilizer. Now, first Z, then Hadamard can be swapped with first Hadamard and then X. So it's just a different order of this identity here. So Z becomes X. And then X at the input of a CNOT becomes XX at the output. So you have XX. And then the XX at the output, and then X through a Hadamard becomes Z. So you have XZ. And then Z on the target of a CNOT becomes ZZ. And then X again changes to Z. And then again, Z on the target of a C0 becomes Z and Z. So you have Z twice, that cancels. And so the output stabilizer is ZZI. So this was super neat. You can just do this with pen and paper as long as you have this cheat sheet. So what was special? The special thing was the input was a stabilizer state, meaning it has poly stabilizers. It has a complete set of poly stabilizers. And then you only had a Clifford circuit, meaning a circuit consisting of only Clifford gates. In those cases, you can easily track these stabilizers to the output. So right now, you don't even have to worry about what this psi is. It's good enough to just know the stabilizers of psi. So you have done this for one stabilizer. You can again take Z on the second qubit and track that Z through the circuit, and you'll get a different stabilizer. And similarly, Z on the third qubit will give you a third stabilizer. And all of those put together will form the stabilizers for the output state. And you have efficiently tracked this state. So this is how you can efficiently track stabilizers in a Clifford circuit. Now, what happens when you do measurements? So we have already seen how to think of measurements. We wrote down the observable, we did this matrix vector product and so on. But the stabilizer formalism tells us how to efficiently think about poly measurements. So for example, let's say you have this bell pair generation circuit, and then you're measuring Z on the first qubit, right? So we already know what the output is, but let's rethink this in the stabilizer formalism. So the first thing you do is you write down the stabilizers for the state before the measurement. So here the stabilizers are generated by X Kronecker X and Z Kronecker Z. Okay, so you have XX and ZZ. Now, and then you are measuring Z on the qubit A, right? So you have ZA. So what the stabilizer formalism for measurements tells us is you take the Z, the operator you're measuring, and compare it with the stabilizers of the state before the measurement. So you see that Z anti-commutes with XA, XB, simply because Z on A and X on A anti-commute. So X and Z anti-commute. And so whenever the measured operator anti-commutes with a stabilizer, the first operator that anti-commutes, you replace it with the measured operator. So you kick away this XAXB from the stabilizer group. You replace it with the ZA and the sign of the measurement result that you got. So if you got a +1 result, you get plus ZA. If you got a -1 result, you put minus ZA. Okay. Now you compare it with the second operator, which is ZA-ZB. But ZA clearly commutes with Z's. And so nothing. So when it commutes, you just retain the stabilizer. You don't make any change. Voila, you have it. So the output stabilizer is given by this signed version of the measured operator and the second original stabilizer. And you can rewrite this by multiplying them in this form. And you can check that for this stabilizer group, the corresponding eigenstate is exactly 0, 0 or 1, 1, depending on which sign you got. And so it's very efficient. You just have to take the measured poly operator, compare it with the poly stabilizers, and see if it commutes or anti-commutes, and just do what is prescribed here. And so we never did any matrix vector product thing, right? So it was super efficient to track this. Similarly, let's say you're measuring Y on the Bell state. Again, you take the measured operator Y, you compare it with XAXB, it anti-commutes, you replace. Now you compare it with ZAZB, it also anti-commutes. So now what do you do? So when the first time it anti-commutes, you replace that operator by YA. Now for the second operator, you cannot again replace by YA. Then you have a trivial stabilizer group where you only have one stabilizer element, but you need two. So in this case, the trick is you multiply the second element by the first element. Because each one of them anti-commutes with Y, the product will commute with Y. And so the resulting stabilizer group is the first one being replaced by YA, but the second one is just a product of XX and ZZ. And then you can manipulate this to get an equivalent representation of this group. And this is the stabilizer for the output state. So you don't even have to worry about what the vector representation of the state is. You have the full stabilizer representation, and that's good enough. And overall, this is what the Gottesman-Kernel theorem tells us. It tells us that if you have input stabilizer states, meaning states, n-qubit states that have n independent Pauli stabilizers, and if your circuit only consists of Clifford gates and Pauli measurements, then the output can be efficiently simulated on a classical computer by just tracking the stabilizers. And so this Clifford gates and Pauli measurements are called stabilizer circuits. So overall, stabilizer circuits with stabilizer state inputs are kind of classical, right? So there's nothing quantum in it because it can be efficiently simulated classically. Okay, so this is the stabilizer formalism that I wanted to introduce. And now, after this poll question, we'll get into error correction. So I just want you to take a moment, maybe a couple of minutes. It requires some calculation. So just follow the rules that I just said, and try to calculate what the resulting stabilizers of this circuit are. Just note that the input is not 0, 0, it's 1 and 0. And so you just have to change things accordingly. So start with the stabilizers of the input and then track it through this circuit. You'll get stabilizers here, and then apply the rules that I just prescribed for measurements.
Meanwhile, can you answer the question online maybe? How can we go from
Sure.
stabilizers to stabilizer states? Or maybe the other way?
Good question. So once you have, so if you have a Pauli operator, or if you have a set of commuting Pauli operators, then they are valid stabilizers. And the way you get stabilizer states from them is you diagonalize them. You find the eigen decomposition of the operators you have. And because they all commute, that linear algebra guarantees that there is a particular eigenbasis that diagonalizes all of the operators you have because they commute. And you just have to find that common eigenbasis, and then those eigenstates that you get will be stabilizer states with respect to those stabilizers. And the other way, once you're given a stabilizer state, you just have to find independent Pauli matrices that stabilize a state, meaning that the state is a +1 eigenvector of these Pauli matrices. And once you find a set of them, if you find an n linearly independent Pauli matrices that fix the n-qubit stabilizer state you have, then you have the stabilizers for the state. So that's how you go between one to the other. So the definitions for the Pauli matrices were given in previous slides, so you can use those definitions. Actually, you don't need the matrix representation for this problem. You just have to track the stabilizers to the circuit. Okay, maybe let's close the poll and see what the results are. Okay, so it seems like maybe things were not as clear. So let me do this again. So what you do for a problem like this is you start with the stabilizers for the input. So the stabilizers for the input, so you know that Z fixes 0. But Z acting on 1 gives -1. So minus Z fixes 1. Okay, so those are the input stabilizers. Now you track this through the circuit. So minus Z on H becomes -X, and Z acting on 0 becomes 0. Now, so these are two independent stabilizers. So minus Z has become -X. Z is fixed, it stays as Z. Now on the C0, if you use the rules, the cheat sheet I introduced before, then X on the C0 becomes XX. So At this point, what happens is the minus x becomes minus xx, and the z acting on the target of the C0 becomes zz. So these are the two stabilizers that you start with at the input of the measurement. And now you have to check what the measurement does. So you're measuring x. So you compare with minus xx, it commutes. So minus xx stays. X anti-commutes with zz. So zz must be kicked off and replaced with x on the first qubit and I on the second qubit. But what's the sign? The result was given as +1, so it's plus xi. Therefore, this is the right option. So this is how you track the stabilizers through the state. You start with stabilizers at the input, you track them through the circuit using the rules I introduced before, and then you use the rules for the measurement to change the stabilizer group. So this was, this might not be easy to pick up on the first go. So I understand, but hopefully the process is clear now. So,
Narayanan, there is a question. Can you address it? Like
yes, I'm just looking at the chat. Okay. Where did Z come from? So at the input, you just find stabilizers for the input. So I already introduced that Z acting on 0 is 0 and Z acting on 1 is -1. So Z acting on 0 is 0. Z acting on 1 is -1. So which means these two are eigenvectors, but this has a -1 eigenvalue. But when you want stabilizers, you only want +1 eigenvalues. And that's why I pulled the minus to this side so that minus Z fixes 1 and Z fixes 0. That's how I got the Z. And then, in this case, so for this problem, there's no Y. Y was an example before, and I is just the identity. So I'll go through the C0 again. So when you have a C0, so the rule that we saw earlier was x at the input of the C0 is the same as first doing the C0 and then doing x at the output, right? And then when you have a minus, the minus just retains. And so that's why when minus x goes through the C0, it becomes minus xx at the output. Adam, hopefully that was clear. So if you check the cheat sheet, you will have this rule for just plus x going through the C0. But when you have a minus, the extra minus just retains there. Okay, so hopefully that problem was instructive. You can see the slides again and do the problem later. But for now, let's just continue with the course. Okay. Yes, now we are getting into error correction. So what are the errors that we want to consider? The errors that we want to consider are poly errors. And the reason we only consider poly errors is because, like I said earlier, poly matrices form an orthogonal basis for all matrices. So if you delve deeper into the representation for quantum channels, or if you, for example, took the short course yesterday, you might have seen that channels are represented using cross operators. And because poly matrices form a basis for all matrices, you can represent any channel in the cross representation where the cross operators are linear combinations of polys. And so effectively, any channel can be decomposed using cross operators, which are further decomposed using poly matrices. And the process of measurement projects you into a poly frame. So the effective error on the state becomes a poly error when you do these stabilizer measurements that I'll talk about shortly. And this is why it's fine to consider poly errors as long as your hardware doesn't have too many correlated errors or too many errors. So there is some caveats, but for typical cases, it suffices to consider poly errors. And so we will just consider poly errors. And so this is a key result. So if you can correct poly errors on p qubits out of the n qubits you have, then any linear combination of them can also be corrected. And there is a recovery operator that can construct. And so for this course, we'll just see how we can construct codes that can correct poly errors. So let's go to the chart. Yes, Ali, if a stabilizer doesn't, if you have a poly stabilizer and if you have a poly measurement, then poly operators either commute or anti-commute. So there's only two possibilities. So if they don't commute, they have to anti-commute. Bob, yeah, so the Z is just, yeah, I guess you just have to, once you get familiar with the simple basis states in quantum information, you will see what those stabilizers are. And so but for the 0 and 1, it's good to remember that 0 and 1 are eigenstates of Z, and therefore either Z or minus Z will be a stabilizer for 0 and 1. And so this just comes from just thinking about it. So if it's not apparent the first time, I think once you see it a couple of times, you'll get used to it. So, but that's the idea. So for simple states, you just remember what the stabilizers are. So I'm just starting error correction. So, all right. So before we construct a code, it's good to revisit this slide where I introduce these Bell states, and then we generalize to the GHZ state. And we are going to now use this GHZ state to construct our first code. So what we are going to do is, this is how you can generate the GHZ state. So think of alpha and beta for now as being 1 over square root of 2. And then if you go through this circuit and write the output state, you will see that the output state is, for general alpha and beta, it's of this form. But when alpha and beta are 1 over root 2, this is exactly your GHZ state, right? So you can produce the GHZ state using this circuit. And by using the this poly tracking rules that I said, you can start with Z's here and track the Z's through the circuit to end up with the stabilizers for the GHZ, which you already know. Now, how does this become a code? So what I've done here is 2 of the inputs are fixed to a 0 state, right? There is no information there. It's just fixed to 0. Whereas this first qubit, I left it as being arbitrary. So it can be any linear combination of 0 and 1. And what you get at the output is this GHZ state. But now, instead of these 3 stabilizers that you had before, this state is stabilized only by the first 2 for any alpha and beta. So let me say that again. For the GHZ state where alpha and beta are 1 over square root of 2, we have already seen that ZZI, IZZ, and XXX, the 3 form independent stabilizers. But when you drop the requirement that alpha and beta are 1 over square root of 2 and make alpha and beta arbitrary, you are effectively dropping the third stabilizer from the group, which means you have created space for a logical qubit. So on a 3-qubit state, if you have 3 independent stabilizers, then it's just a one-dimensional space, or a 0-dimensional space actually, where you have a fixed state. Whereas when you drop this XXX, you have only 2 stabilizers on 3 qubits, which leaves room for 1 logical qubit, and that's exactly this input here. And so this is how you can change the GHZ state into a code state. So for the code, you have 2 stabilizers. We already know they commute. And this psi bar is a +1 eigenvector of these 2 stabilizers for any alpha and beta. So what you can do is, if you have 1 qubit of information where you picked some alpha and betas to store your information, then you can encode it into this 3-qubit code using this circuit. And the output will be alpha 000 plus beta 111, where your information is still contained in alpha and beta. And you know that for any information that you encode, ZZI and IZZ will have +1 eigenvalue with this code state. And that's the definition of a code. Hopefully that part was clear. So that's how you encode 1 logical qubit of information into 3 physical qubits. And the way you know that the state is a code state is if you measure the stabilizers, if you measure Z Kronecker I, or I Kronecker Z, you are supposed to get +1 because you know that these are +1 eigenvectors. And so that's how you encode into the code. Now, how do you detect errors? So you have encoded into the code, right? So at this point before the X, this is a perfect code state. Now let's say some error happens. Let's say the error X happens. We said that we'll only consider poly errors. Let's say the error X happens on the first qubit. Then the state actually changes to this superposition, right? So 0, 0, 0 becomes 1, 0, 0 because the X flips the first 0 and the first 1 here. Now what you do is you measure the stabilizer generators ZZI and IZZ. And here I've shown the measurement circuits in sequence. Right, so previously we had the linear algebra description of measurements where we took the observables, we diagonalized them, and so on. But here I'm just directly showing you the circuit. Now, once you have the circuit, you basically initialize an ancillary qubit in the 0 state. And then because you have these ZZ stabilizers, ZZ elements of the stabilizer, you put a C0 from the data qubit to the target. And similarly, Z on the second qubit. So you have the C0 from data qubit to target, and then you only have identity on the third qubit, so you do nothing. So you have two C0s from data to target, where the target is initialized in the 0 state, and then you measure the target ancillary qubit. So what happens? We already know how X propagates through C0s, right? So we just check that X at the input of a C0, at the X at the control input of the C0 propagates to XX here, meaning that the X is actually propagating to the ancillary qubit and it will flip it. And because it flips it, when you measure Z, you get a -1. And that's how you know something went wrong. Because if there was no error, when you measure these ancillars, you will get +1. And you can verify that later. But when you have an error, you can propagate the error through the circuit, and you will see that it flips the measurement result to -1. So whenever you get a -1 in one of these measurements, you know that something is wrong. And that's exactly your syndrome in the quantum case. So you get 2 bits of syndrome, and if both of them are +1, then you're fine. If either one is -1, then there is some trouble that happened, and you need to find out what is the most likely error that happened given the syndrome. And this is how error correction works. So just to reiterate, error correction stems from commuting poly operators, which we call stabilizers. And the +1 eigenvectors of those commuting stabilizers form our code words or the code states. And then you measure stabilizers, and you need to get all +1 results to be sure that the state is in the code space. If any result is -1, then the state is outside the code space, and you need to bring it back to the code space by doing a correction operation. Okay, so I've just summarized what I just told. So the error propagates through the C0 and flips the Z. And you can see, for example, if you have X here, as well as you had an X here, if you had 2 X's, then this X will propagate as XX, and this X will propagate as XX again, and this X and this X will cancel, right? And then the measurement will not flip. And the error has actually tricked you, because 2 X errors actually cancel off and don't flip the measurement. And so you can only detect some of the errors, right? So the number of, so that's what I've said here. So the measurement results in -1 whenever there are an odd number of X's on the ancilla through the C0s, right? So if you have an even number of X's propagating through the ancillas, then they cancel, and you won't see that in the syndrome. And another way to say this is that whenever, and you know that poly operators either commute or anti-commute. And so another way to say the statement is that when the error anti-commutes with the stabilizer, you get a -1. Here in this case, you had 2 X's. So, but the stabilizer also had 2 Z's. And so the 2 X's commute with the 2 Z's. And that's why you did not see a -1. If you had an odd number of X's on the first 2 qubits, then you will only anti-commute with one of the z's, and so you will see a -1. And so whether an error flips the syndrome bit or not can just be detected by its commutativity with the stabilizer. Okay, so now just a quick exercise. So if you have the same two stabilizers, what is the syndrome for the error IXI? So if you have an X error on the second qubit, can you tell me what the 2 bits of the syndrome are? This should be pretty quick. Okay, we can close the poll, I think. Yes, -1, perfect. Most people got it. So X on the second qubit, anti-commutes with both stabilizers, and you get -1. Perfect. Okay, so now let's jump to a very useful representation of polymatrices. So you have, let's say, an n-qubit Hermitian polymatrix. For example, here I have X tensor Z tensor Y. Now we are going to map this into a pair of binary vectors, A and B. And so how do you define the binary vectors? So this is just a convenient representation of polymatrices, and this forms the crucial connection between quantum error correction and classical error correction. So if you have X, Z, and Y, so you have two vectors A and B, and each bit of the vector corresponds to that particular qubit. So whenever you have an X, you put a 1 in A and a 0 in B. Whenever you have a Z on a qubit, you put a 0 in A and 1 in B. Whenever you have a Y, we know that Y is a product of X and Z. And so, oh, there's a typo here. This should be 1. So this should be 1, 1 here. Okay. So, so whenever you have Y, you have 1 on both A and B. So A is basically the X component of the polymatrix, and B is the Z component. So it's a very simple mapping, but it's a very useful mapping. So now we know that polymatrices commute or anti-commute. So for example, you have two polymatrices here, EAB and ECD. One is XZY and the other is ZZX. Now we know how to check commutativity, right? So you know that X anti-commutes with Z, Z commutes with Z, Y anti-commutes with X. So you have two anti-commutations. So you have X and Z anti-commuting and the Y and X anti-commuting. So overall, these two matrices commute because you pick up two -1s and they square to 1. Now, how do you do this in the binary space? First, you map these to the corresponding binary representations. So you have XZY and ZZX. Right. So again, I made the same mistake. So there's a 1 in the last component here. So it's 0, 1, 1. And then this symplectic inner product basically tells you if the matrices commute or not. So what you do is you take the X component of the first vector, and then the Z component of the second vector, and then you take the binary inner product. And then you take the Z component of the first vector and the X component of the second vector, and you take the binary inner product, and then you sum them modulo 2. If the result is 0, then they commute. If the result is 1, they anti-commute. So it's a very simple check. So you just have to do some simple vector inner products modulo 2, and that tells you if the matrices commute or not. And you can check that this works for this case. So now let's go back to our stabilizers. We have ZZI and IZZ, which means our binary representations will have zeros for both A's, because A is the X component and there are no X's here. And then B is the Z component, and you have ZZI and IZZ. Now let's say you have the error XII, which means you have just 1 in the first bit of the A part and 0 in the B part. And now you do the symplectic inner product to check the syndrome. So if you check commutativity of the error with the first stabilizer, ZZI, you do the first inner product, which I've shown below. And you see that the result is 1, which means the error anti-commutes with the first stabilizer. And with the second stabilizer, you can see that the symplectic inner product is 0, and so the error commutes. And so so instead of the syndrome being -1 and +1, we have just changed from this BPSK format to the binary format. So whenever you see a 1, it means the error anti-commutes. Whenever you see a 0, it means it commutes. Okay, so that's how you map poly matrices to the binary space and check commutativity and anti-commutativity. Now let's put them together in the form of a matrix. So here is our quantum parity check matrix. So you have two stabilizer elements. So you have the first one, which is ZZI. So you have zeros for the X part and ZZI. And the second row is IZZ. And you can split this into two halves. So the left is the X part, which I'm calling HA. And the right is the Z part, which I'm calling HB. Now, the first thing is the stabilizers must commute, which means the symplectic inner product of the stabilizers with itself and the stabilizer with other stabilizers should be 0. And that symplectic inner product constraint can be written in this form for HA and HB. So this is just the stabilizer commutativity constraint. And then the syndrome is simple. So you just take this HA, HB, and then you flip the X and Z parts of the error. And then you do HA D transpose plus HB Z transpose. Again, everything is modulo 2. So now you see how we have gotten to a similar form that we had for classical error correction. For classical error correction, we had a received vector Y, and then we computed the syndrome as H times Y transpose. Here you have the error given by C comma D, and then you just do the symplectic inner product with the quantum parity check matrix, and that gives you the syndrome. So it's very similar to classical error correction, just that it's a different inner product. Okay, so we have seen this. And now what are the code words of this code? So for the classical case, code words were those vectors that satisfy all the parity checks, meaning that the syndrome for the code word will be 0. Similarly, in the quantum case, you know that the stabilizers will have 0 syndrome because stabilizers commute with each other. And so if you measure the stabilizers, that's how it works. But there are also non-stabilizer vectors. For example, I've shown you 2 of them here, which also commute with the stabilizers, but which are not themselves stabilizers. So 111, 000 and 000, 100 for this particular example are vectors that commute with the stabilizers. They have symplectic inner product 0, but they are not themselves stabilizers. And this is what we call as logical operators. And the minimum distance of the code is the minimum weight of any logical operator. So in this case, the weight of the Z is just 1. And so the weight is just defined as on how many qubits are you applying non-identity or non-trivial poly matrices. So this is applying Z on the first qubit, and so the weight is 1. This is applying X on 3 qubits, so the weight is 3. And so for this particular code, the minimum distance is 1 because it's the minimum weight of any code word, and this is a code word. Right? So code words are basically those poly operators or in the binary vector representation, binary vectors that commute with all the stabilizers, that have symplectic inner product 0 with all stabilizers, but are not themselves stabilizers. Okay, so again, I've repeated the parity check matrix for the code. Can someone quickly, can you all answer quickly what's the syndrome for XXX? You can do it in the binary way, or you can do it in the standard poly way.
Narayanan, once you have answered, once the poll is done, Ali has a question. If you can elaborate on how correlated errors degrade poly error correction techniques using a simple code like 3-qubit code you presented.
Yeah, great question, Ali. Yeah, so when you have correlated errors, sometimes if you know the correlations that are there in your hardware, meaning that, for example, if you know that an X error on the first qubit is always followed by an X error also on the second qubit, then you can modify your decoder to say that, oh, whenever you see this syndrome, don't think that it's X only on the first qubit. It must actually be X on both qubits because that is more likely. So you can actually program these kind of correlations if you know them a priori. But if you don't, if you think that you have only uncorrelated errors, but there are correlations, then your decoding is not going to work well. And you just need to do like tomography or like do enough kind of noise characterization to get a good noise model that represents the hardware, and then design codes accordingly. Okay, so let's close the poll. I think it should be pretty simple. Okay, so many people were not sure. So so here the stabilizers are, again, if you just think of this as in the poly space, the stabilizers are still ZZI and IZZ. And so you can just do what you did before. So if you have XXX, then you have ZZI with XXX is the same as XXX times ZZI. Simply because Z and X anti-commute, C and X anti-commute. And so you have 2 -1s that become +1. And or you can just take the vector representation of XXX, which is 1, 1, 1, 0, 0, 0. And then you can do the symplectic inner product of this with each row. And so you can do it either way, but in this case, you will see that 0, 0 is the right answer. Okay, so let's keep going. Okay, so now we have seen the matrix representation for stabilizers, and we have seen this 3-1-1 code. So in this slide, I've just summarized everything that I've told so far. And the distance of this code is 1 because the minimum weight of any logical operator is 1. And so these are the stabilizers, and these are the logical operators, these X bars and Z bars. And now what I'm going to show is how you can use the stabilizer formalism that I introduced before to arrive at these operators. So for example, if you have the encoding circuit for the code, you can start with Z at the input on one of the ancillas, because you know it's a stabilizer, and you can track through the circuit, and you will end up with stabilizers for the output. Similarly, if you start with X on the logical qubit, so this was the example of a stabilizer, and here is an example of a logical operator. So if you have X on the logical qubit, you can again track it through the circuit, and you will get the logical operator on the code word, right? And so the stabilizer formalism that I introduced before can just be applied to these encoding circuits to track these Z's and X's on ancillas and the logical qubit. So when you take Z's on the ancillas and propagate, you get stabilizers. When you take X or Z on the logical qubit and track that through the circuit, you get the logical operators. Okay. So now, so we briefly saw the Hamming code before, and here I'm just showing you a quantum example of quantum version of the Hamming code, which is called the Steen code. So we already saw that a quantum parity check matrix has 2 parts, HA and HB. And in this particular case, we are just doing a special example where this quantum parity check matrix has a block diagonal form. So the first half, the top half of the matrix, we take it to be H and 0. So when you map this to the binary space, it means that this only when you map this to the poly space, this only gives you X type operators because the Z part is fully 0. And this H is just the Hamming code parity check matrix. Similarly, the bottom half has H on the Z part and 0 on the X part. So these rows give you only poly Z type operators. And you can, because you know that HH transpose is 0, you can check that these give valid stabilizers. So just to be clear, the first row, for example, so if you take the first row of H and apply it to the top half here, if you have this comma 0, then this actually, so this first row actually maps to X1, X4, X6, X7, right? So this will be the first row here. The first row of here will be a purely X-type operator given by the first row of the Hamming. And similarly, you can go through other rows. And similarly, for the bottom part, this will exactly give you Z1, Z4, Z6, Z7, and similarly the other rows. And so this is why it's nice to have this binary representation, because you can borrow from classical codes and build quantum codes. And similarly, the logical operators for this code, you can verify that these are given by these two vectors. And these will satisfy all the conditions that we saw before. All right, so now we have seen error correction in the general case, and we looked at the 3-qubit example. For this, and we have already seen this standard array decoding that Professor Vasic introduced for the classical error correction part. And you can do exactly the same thing in the quantum case. So you can write down the different possible low weight error patterns, and you can write the different syndromes that you get. And you can build a similar standard array, and then you can map, instead of the received vector, in this case, you will have different error vectors. So depending on what syndrome you have, you can build a standard array to map it to a most likely error. But again, the complexity scales exponentially. So this is just a repetition of what I just said. What you would do is, once you have the parity check matrix, you will compute the syndrome, which is just symplectic inner products of each row of the parity check matrix with the error vector C, D. And then syndrome decoding means that given the measured syndrome, you determine the most likely error that matches the syndrome. So for example, going back to Ali's question, if you know of correlations in your hardware, then you would put that information into the decoder, and then it will guess the most likely error patterns according to those correlations. But again, if you do this naively, the complexity still scales exponentially. Okay, so this is a poll question. Maybe I'll skip in the interest of time, but you can. This should be pretty easy with all the tools that I've introduced before. So you can check this later. Okay, now let's generalize what we just did for the Hamming code. So for the Hamming code, we had H0 and 0H, but you don't have to have the same H on both sides. And this is the so-called CSS construction, where you can have a different parity check matrix for the X-type stabilizers and different parity check matrix for the Z-type stabilizers. So you have HX and HZ, but of course, the symplectic inner product constraint says that HX and HZ should be orthogonal. And then the logical operators will be all vectors C, D that don't represent stabilizers, but they still commute with all the stabilizers. So they have symplectic inner product 0 with stabilizers. Whenever you have an error, you again compute the syndrome as a symplectic inner product with this H matrix. And finally, the parameters of the code are given by, n will be the same number of bits that are there in your classical code. So let's say the classical code CX has n bits, then the quantum code has n qubits. The dimension of the quantum code is constructed from the dimensions of the classical codes CX and CZ, which I represent as K sub X and K sub Z. And you can do some calculation to arrive at this result. Finally, the minimum distance of the quantum code is given by the minimum weight of vectors in this union space. So the first space is the code CX minus the dual code of CZ. So you can actually check that the dual code of CZ will be a subcode of CX, meaning that it will be inside the code CX. And so if you just eliminate CZ dual from CX, and then similarly CX dual from CZ, and look at all vectors in the space and compute the weight of the poly weight of those vectors, the minimum poly weight gives the minimum distance of the code. And so this is just a nice construction that borrows from classical codes, the key constraint being that these two matrices must be orthogonal to each other. And so a standard example is the surface code, which can actually be constructed from repetition codes, but I won't get into the construction. So visually, it's just you can just lay it down on a 2D lattice. So here I've laid down these. So all these white circles represent our data qubits. The blue squares represent the Z-type stabilizers checks, and the red squares represent the X-type stabilizer checks. So for example, let's do one here. So if you take this particular blue check, what it says is that Z on this qubit, this qubit, this qubit, and this qubit. So this is a weight 4 Z operator that should actually stabilize the state. So if you measure Z, 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 you should get +1. Similarly, for all of the blue squares, if you just measure Z, 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 Z on the 4 neighboring qubits, then you should get +1 simultaneously. Similarly, for the x, for this x, for example, if you measure x, you should get +1. Similarly, for all the other x checks. And so this is what defines the surface code. So if you have an L by L lattice, then the number of white circles you will have is roughly on the order of L squared. And the minimum distance of the code will be L, because you can check that the logical operators are just these string operators. So for example, if you do Z, 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 this weight 5Z operator, then you can check that it commutes with all these blue and red checks, but it's not itself a stabilizer. And so it is a logical Z. Similarly, the logical X is X, 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 X. And that also satisfies the same constraint. And they meet at one point, which means these two anti-commute. And so these are the logical operators, and the weight of the logical operator gives the distance. So in this case, this is a 5 by 5 lattice. So the distance is 5, and the surface code encodes only 1 qubit. And so this is the surface code, and people have simulated the surface code with a very good decoder. And here we are just sweeping down physical error rates. So each number on the x-axis means that a poly error can occur with this probability, either x or y or z. And then with 1 minus this probability, no error occurs. And then the time to failure is basically 1 over the output error probability, or the frame error rate, meaning that 1 over this number is the probability that you still have some residual errors after doing decoding. And the important thing is that as you increase the size of the lattice, the distance increases, and you get a threshold, meaning that if the physical error rate is less than the threshold, then you can make the code live, that you can make the time to failure arbitrarily large, meaning that the code survives arbitrarily long. Whereas on the other side of the threshold, the code becomes worse and worse as you increase the size. And this is the phenomenon of a threshold, and getting a high threshold is very important, and that's something that error correction people actively work on. So I will also skip this poll question in the interest of time. So just some final comments on these slides. So now we have seen how you can take k logical qubits and encode them into physical qubits. But now you're building a quantum processor, a quantum computer, for example, which means that if you do logical operations directly on the information qubits, then these will be noisy, and so you cannot guarantee that the output is in the code, right? You cannot guarantee that the output is the right thing, because noise could have corrupted the computation. So what you do is you first encode the k logical qubits into n physical qubits. Then you apply physical operations on these coded qubits, and these must be fault tolerant, meaning that if there are errors that occur, the code should be able to correct that. And then finally, when you're done with the computation, you then decode, and hopefully if all errors were corrected properly, then you end up with the desired final state. So for this process to work, two things need to work. One is this, you need to first translate any operation that you want to do on the k qubits into the right operation that you need to do on the n qubits that will induce this k qubit operation. So you need to first do this translation and then make that translation fault tolerant. So there is this logical computation aspect of quantum processing, where you have to map these logical operations to physical operations. And on the second thing, you have to correct errors on these physical circuits. And so we didn't go too much into this logical operation part, because that will take its own short course. But it's a very important process that is to be done. So you have these universal gates that we introduced before, and you need to be able to do these universal gates on these k logical qubits. So for each of these gates on each of the logical qubits, you need to translate them into n qubit physical operations that will induce these desired logical operations. Finally, we get to quantum LDPC code. So we already introduced this CSS construction, and you can take these LDPC codes that Professor Vasic introduced in the classical error correction part. You can take those parity check matrices and build quantum codes like this. But the key problem is they have to be orthogonal to each other, and this is very hard. So finding an LDPC parity check matrix, two parity check matrices that are mutually orthogonal is quite hard. But people have come up with very clever constructions, and We have listed some of the names here. So if you go to Google Scholar and type these names, you will find the relevant papers. And quantum LDPC codes are the surface code is itself actually an example of an LDPC code, but there are more better constructions of quantum LDPC codes that have come out recently, just in the past 1 or 2 years, that give optimal parameters and that can actually that are actually very promising to for scalable quantum technologies. Finally, these LDPC codes can still be iteratively decoded using this min-sum algorithm or the belief propagation that Professor Vasic introduced before. But now everything is done from the syndrome perspective, meaning that you measure the syndrome in hardware and feed the syndrome as the input to the decoder, and then the decoder computes the error pattern that is most likely to have occurred and satisfies the syndrome. Yeah, and so I will leave this as well. And so to summarize, if you just compare error correction in the classical and the quantum case, in the classical case, we decoded based on the receive vector. But in the quantum case, like I just said, you only have the measured syndrome to decode off of. And then in the classical case, any sparse parity check matrix gives an LDPC code. It might not be a good one. You might have to carefully design, but in the quantum case, you need 2 such sparse matrices that are orthogonal, and this is quite tricky to do. In the classical case, only the 0 vector has trivial syndrome, meaning that if you have the all 0 vector as the error, then the code word plus error is just the code word, and then if you do H times Y transpose, you will get zeros. Whereas in the quantum case, even if you have stabilizer errors, that don't change the syndrome, right? Because stabilizers themselves have 0 syndrome. And so this is called the degenerate errors, which is also a big topic, but we didn't get into that in this short course. And finally, in the classical case, our transistors are really good. So the classical computers that we use today don't require that much error correction, although storage devices and other things need. Whereas in the quantum case, all these gates that we are building today are noisy across all technologies. And so you need to do both decoding and error correction, as well as this logical computation in a fault-tolerant way. So some closing thoughts. So degeneracy is a key advantage in the quantum case, but we haven't found good ways of exploiting it efficiently. And can we construct efficient algorithms that that correct many errors? That's an open problem. How do we take these recent quantum LDPC constructions and build them in hardware? That also seems quite challenging, but they will be necessary in the long term to build scalable systems. And finally, can we get to universal fault-tolerant operations on these LDPC codes? These are all very much open problems that have an equal amount of importance both in quantum computing as well as quantum networking and repeaters. So with that, I think we will close the course, and I'm happy to answer any questions. So to answer Bob's question, so I think Asit is answering it, but yeah, so for when you do quantum logical gates, you have to do error correction on top of the logical gates, because you take the logical gates and you translate them into physical gates that you do on the coded qubits. And then if errors occur during the gate operation, then you have to fix errors. So you have to combine error correction with the logical gates. So Mark's question. So with this graphical approach, can't I? So I'm not quite sure what Mark's question is. Mark, could you elaborate on your question, and then I can answer that? So Ali's question, yeah, why are wrong edge corrections a challenge? So so if you go back to the surface code, if you're thinking of building this in the hardware, then it means that you need to implement these checks only to neighboring qubits, right? So you only interact these neighboring qubits, and so these are geometrically local qubits. And this is easier to build in hardware, because imagine you're IBM and you're building like a superconducting quantum computer, and you need to build wires that connect these qubits and do CNOTs. And so it's easier to do if they are geometrically local. Whereas for these optimal quantum LDPC codes, you might have to interact the white qubit here with the white qubit there. right? These long range connections, you have to have wires going around, or you have to, move this white qubit for, briefly, you have to move it close to this qubit, do the interaction, and then take it back. So there are these extra overhead that are quite challenging to build in hardware. And how to exactly balance this locality with, optimality is very open. Yes. So, okay. So good question, Mark. Yes. So for example, for the surface code case, let's say because your syndrome measurements are also quantum circuits. So your syndrome measurements can themselves be noisy, right? Because you have these C0 gates that are connecting the data qubits to the ancillary qubits. So let me go back to. Yeah. So for example, when you're doing this measurement, so the C-naughts themselves can fail, or there can be extra errors on the ancilla and so on. So in this case, you might have to repeat the syndrome measurement. For some decoders, you have to repeat the syndrome measurement, and you have the time history, and then you use the time history to cleverly decide what was the actual data error and what was the error on the ancilla and so on. And so people do construct these kind of 3D graphs to do matching algorithms for decoding surface codes, where each layer of the graph is like a time layer, right? So there's a 2D space layer, and then you have time layers, and then they combine both the space and time information to decode. But there are also other codes for which Professor Vasic, Nitin, and Asit have built decoders where you don't have to repeat the syndrome measurement. You can actually do single shot error correction, which means that you can get one set of noisy measurements and still come up with a reliable estimate of the error. And so, but these are all quite open questions. Good question. Any other questions that people have?
So if there is no more questions, maybe we can conclude the course. Thank you very much to everybody who participated, and hopefully you learned something. And this is the quite open area. A lot of things are happening every day. New papers are appearing. So hopefully we covered basics, and there is much more to learn.
Yeah, absolutely. And if you have any questions or comments, please feel free to email us and can answer them.
Wonderful. Thank you, Narayanan and Bane. We appreciate you taking the time to put the course together and then teaching it today as well. And to our moderators, thank you for helping out in the Q&A. I think that worked really well. We will have the recording and slides available within the next week or so as we do some quality editing on them. And those will all be communicated via email. And I think from there, we'll go ahead and end the webinar and ask that you take the time to do our post lecture survey that will help us as we develop future programs.
Thank you, Brenna. Thank you for organizing
Thank you all.
this together.
Thank you.
Thank you, Brianna.
Thank you.
Yeah, so I think there are some updates to the slides. So we will, when Brianna sends out the new version of the slides, it will be up to date of what we presented today.
Yeah, we'll do one big final package.
Yeah, thank you.